What exactly is a star? A tiny point of light in the night sky, or a vast living engine burning for billions of years? Tonight we're going to follow the story of how stars are born, how they live, and how they die. A story written in light and silence scattered across the galaxy. Hello and welcome to the Sleepy Astronomer. If you're here to unwind, to quiet the mind, or to drift gently towards sleep, you're in the right place. Before we begin, I'd love to know, where in the world are you watching from tonight? It's always fascinating to see listeners tuning in from every corner of the planet, all connected beneath the same sky. And if you enjoy these calm journeys through the universe, it would mean a lot if you could leave a like and subscribe. To those already subscribed, thank you. You're helping this little corner of the cosmos stay bright. Now, I do hope this video doesn't end up being too interesting and keep you awake. But if it does, at least you'll have learned something about how the universe works while you drift in and out of consciousness. So settle in, get comfortable, and let's begin the quiet story of starlight. What really happens inside those distant suns? And what do their lives tell us about our own? Every light you see in the night sky is a memory. Some began their journey before the first humans walked the earth. Others left their stars when dinosaurs still roamed. Each photon, each grain of light, is a messenger from a distant sun, carrying the history of its creation. A star is not a thing that burns, but a balance that endures. Inside, gravity pulls matter inward, while pressure pushes outward. Two ancient forces locked in perfect harmony, and at the center, tiny atoms combine, releasing energy that radiates outward as warmth and light. It's a process so steady that even our own sun, after 4.5 billion years, is only halfway through its calm and ordinary life. But there is nothing ordinary about what stars make possible. They forge the elements of everything we know: the carbon in your breath, the iron in your blood, the calcium in your bones. Long before Earth existed, stars were already at work, creating the ingredients for oceans, air, and life itself. In the stillness of space, they are born in darkness, deep inside clouds of dust and gas so cold that light barely escapes. Over time, gravity pulls those clouds together, forming the bright hearts of new stars. These stars shine for ages beyond comprehension, until, one day, their balance begins to fail. Some fade quietly, others end in great bursts that seed the galaxy with the building blocks of worlds, and from their ashes, new stars rise again. Astronomers have pieced together this grand cycle by reading starlight itself. Through tiny variations in color and brightness, we can tell a star's temperature, its age, even the atoms swirling inside it. With patience, we've come to understand that stars aren't eternal. They live, they change, and they pass their gifts forward in an endless chain of creation. So tonight we'll travel through that chain, from cold clouds to newborn suns, from gentle giants to dying embers. We'll see how stars shape galaxies, how they breathe out the elements of life, and how their deaths give birth to new beginnings. Every ending in the cosmos, it turns out, is also a beginning. Far from the warmth of any nearby star, there are regions of space so cold and so quiet that they seem almost empty. But these are not voids, they are nurseries. Inside them, the next generation of stars is waiting to be born. Astronomers call them molecular clouds, and they are among the darkest, most mysterious structures in the galaxy. If you could drift through one, you would see almost nothing at all. Even the nearest stars would fade behind curtains of dust so thick they swallow visible light whole. Only faint infrared glows or distant radio whispers reveal that anything is there. These clouds are vast beyond imagination, Some stretch across dozens or even hundreds of light years, containing enough material to create thousands of suns. Yet their gas is spread so thin that, on average, a cubic meter might hold only a few hundred molecules, a better vacuum than any laboratory on Earth could make. What makes them special is not how dense they are, but how cold. Temperatures hover only a few degrees above absolute zero, cold enough that hydrogen, the most abundant element, pairs up into molecules rather than floating freely. Traces of carbon monoxide and tiny dust grains add just enough opacity to keep the starlight out, allowing the interior to remain chilled and still. Within that deep cold, gravity begins its quiet work. A small region may, by chance, become a little denser than its surroundings, perhaps due to a passing shock wave or the turbulence stirred by nearby stars. That tiny imbalance is enough. Gravity tugs ever so slightly harder on that denser spot, pulling in more gas, which increases its pull further. The process feeds on itself, growing denser and denser until a faint core begins to form, invisible yet inevitable. Across the Milky Way, many different events can set this process in motion. Sometimes the death of a massive star plays a part. When a supernova explodes, its shock wave races outward, compressing any nearby clouds in its path. Elsewhere, the slow movement of a galaxy's spiral arms acts as a kind of cosmic traffic jam, bunching up gas and dust as it sweeps through. Even collisions between smaller clouds can trigger collapse, piling up matter in new knots. Wherever there's a small imbalance, gravity is waiting patiently to take advantage of it. For collapse to continue, though, the cloud must stay cool. If it warms up too much, the motion of particles inside will push outward and resist gravity's pull. Cooling happens thanks to molecules like carbon monoxide, which radiate energy away as faint infrared light. Dust grains help too, absorbing energy from collisions and emitting it as heat that drifts into space. The lower the temperature, the slower the particles move, and the easier it becomes for gravity to draw them inward. In a sense, starbirth begins not with fire, but with a deep and lasting chill. Inside these clouds, structure emerges like lace, long filaments and tangled threads of gas twisting together. Observations from telescopes like Herschel have shown that filaments are everywhere, weaving through molecular clouds like veins of lightless smoke. Along these filaments, the densest regions form beads or knots, the places where stars will one day ignite. Each knot may hold enough material to make one or several suns, and the entire web of filaments may one day light up as a small star cluster. Yet despite their potential, these clouds are astonishingly fragile. The same turbulence that stirs them can tear them apart. Nearby young stars, through radiation or stellar winds, can strip them down before many new stars form. In this way, the galaxy keeps a balance. Not every cloud becomes a nursery, and not every dense knot makes it to starlight. The process is selective, patient, and endlessly repeated over cosmic time. If you could somehow travel inside one of these regions, it wouldn't look like the bright, glittering images we often see in photographs. To the human eye, it would be pure darkness, a void filled with faint outlines of drifting dust. But with sensitive infrared vision, you might glimpse the faint red glow of warm hydrogen molecules colliding, or the dim shimmer of starlight scattered by tiny particles. Here and there, you'd find spots where the cloud thins, allowing distant stars to shine faintly through. The airless silence would be complete, but within it, matter is quietly gathering, preparing for something extraordinary. Over millions of years, gravity continues to draw material inward, Denser knots pulled from their surroundings, forming embryonic cores. Some merge, others stay solitary. Within these invisible cocoons, pressure and heat begin to rise, signaling the earlier stages of a new star's life. The process is so gradual that if you could watch in real time, you would see nothing changing at all. But step back a few 100,000 years at a time, and you'd see clouds slowly sculpted into denser shapes, as if the universe were sketching with invisible hands. Every star we see in the night sky began this way, a quiet clump in a dark molecular cloud, chilled to near nothingness, gathering its strength through stillness. The heavy elements made by earlier generations of stars, oxygen, carbon, nitrogen, mingle with the primordial hydrogen left from the Big Bang, forming the raw ingredients for the next cycle of creation. It's a recycling system older than galaxies themselves, and one that continues right now in countless hidden corners of the Milky Way. These molecular clouds are the galaxy's great reservoirs of possibility. They hold the dust that will become planets, the gas that will fuel suns, the molecules that may someday become breath and life. They are as silent as the space that surrounds them, yet within their depths lies everything that will ever shine. If you look up at the night sky and see a dark patch where no stars appear, you might just be gazing at one of these places, a shadow against the stars, quietly waiting to give birth to new light. In the quiet heart of a dark cloud, gravity continues its slow and steady work. What began as a faint knot of gas has become a compact sphere, drawing in more material from every direction. The atoms falling inward pick up speed, and when they collide they create heat, not the bright flame of a finished star, but a deep hidden warmth. The center grows hotter and denser, forming the first outline of what will become a new sun. This is a protostar, the cosmic equivalent of an embryo, not yet shining by fusion, but alive with potential energy. As the cloud continues to collapse, it starts to spin. Even the tiniest rotation at the start is amplified as the material shrinks, much like an ice skater pulling in their arms. That spin flattens the gas around the forming star into a thin, swirling disk. It's not a smooth record of light, but a turbulent mix of gas and dust orbiting faster near the center and slower at the edges. From this disk, both the star and any future planets will draw their material. In its midst, the protostar sits like a glowing pearl in a whirlpool of mist. Inside, gravity presses inward with relentless strength, while the gas resists with increasing pressure. This invisible battle heats the core further, sometimes reaching several thousand degrees. The heat cannot escape easily, so the protostar begins to glow faintly in infrared light, still invisible to human eyes, but shining softly in the wavelengths that only telescopes can see. The energy comes not from nuclear fusion yet, but from the sheer act of falling matter converting motion into warmth. The swirling disk plays a crucial role in this process. Streams of gas spiral inward, feeding the growing star, while angular momentum, the tendency of spinning objects to resist changes, prevents all the material from crashing directly into the center. Instead, some is funneled along magnetic field lines toward the poles, where it is blasted outward as narrow, high-speed jets. These jets can stretch for light years, carving clear paths through the surrounding cloud. To distant observers, they appear as delicate, glowing beams, a newborn star's first dramatic gesture. It is almost as if the star, frustrated by the chaos of its birth, tidies its nursery by sweeping the excess material away. The balance between gravity and pressure is not yet complete. The protostar swells and contracts repeatedly, sometimes puffing up as in falling material collides with its surface, then shrinking again as it radiates heat into space. It's a phase of instability, where every gain in mass or energy sets off a small reaction in the opposite direction. Over time, this back and forth calms down as the inner layers adjust, finding a rhythm that will later define the star's stable life. The chemistry within the surrounding disk is already changing. Dust grains bump and stick together, forming larger clumps. Icy coatings form on particles as they drift through colder regions. Molecules like water, carbon monoxide, and methane appear simple but essential ingredients that will one day shape planetary systems. The disk grows thinner as material either falls inward or gets blown away, leaving behind pockets of gas and dust that swirl gently in orbit. If you could watch this process unfold, it would seem almost peaceful, but in reality it's wildly chaotic. Supersonic shock waves ripple through the gas. Magnetic fields twist and snap, releasing bursts of energy. The newborn star flickers in brightness as its feeding rate changes, sometimes flaring brighter for a short while before dimming again. Some young stars experience dramatic bursts, briefly increasing their luminosity 100-fold as massive clumps of material suddenly plunge inward. It's the universe's slowest yet most spectacular light show, written across thousands of years. At this stage, the star is roughly halfway through its transformation from cloud to stable object. It's still gathering mass, still shedding its cocoon of gas, and still adjusting to the pressures building inside. If stars had personalities, this would be their awkward teenage phase. Unpredictable, dramatic, and occasionally messy, but showing hints of the brilliance to come. As more gas falls in, the core temperature continues to climb. Once it reaches roughly 10 million degrees, the hydrogen atoms at the center will begin to fuse into helium, releasing a steady stream of energy. This will be the moment when the protostar truly becomes a star. But even before that happens, its glow is enough to influence its surroundings. The radiation warms the nearby gas, while the stellar winds, streams of charged particles flowing outward, begin to push back against the remaining envelope. Slowly, the jets and winds clear away the last traces of the birth cloud, revealing the young star to the wider galaxy. Around it, the remnants of the disk settle into quieter motion. Material that doesn't fall into the star will remain in orbit, slowly forming rings and clumps. In time, these will give rise to planets, moons, and asteroids, the debris of creation that turns into future worlds. For now, though, the focus remains on the star itself, still forming, still finding balance, still learning how to shine. Astronomers can observe this entire sequence through infrared and radio telescopes, which can peer through the dusty shrouds that block visible light. What they see matches the models beautifully. Swirling disks, collimated jets, flickering outbursts, the telltale signs of stellar infancy. Each young star tells the same story, with variations depending on its mass and environment, but always with the same pattern of gravity, heat, and rotation sculpting order from chaos. The scale of it all is staggering. The process that began as a diffuse wisp of gas now forms an object only a few million kilometers wide, yet bright enough to illuminate its surroundings. The conversion from cloud to star takes just a few 100,000 years, a heartbeat on cosmic timescales. And in that heartbeat, the quiet darkness gives way to the first true light of a newborn sun. What began as a whisper of gravity has become a self-luminous being, glowing softly in the dark. The protostar will continue to adjust and refine its balance, gradually approaching the steady state that defines a main sequence star. For now, it is still cloaked in wisps of dust and faint light, still shaking off the remnants of its birth. But one day soon, it will emerge fully into view, the galaxy's newest lantern, lit by the oldest forces in the universe. At last, the long tension between gravity and pressure reaches a truce. The protostar's core, now unimaginably hot and dense, becomes a natural laboratory where hydrogen atoms collide with enough force to merge into helium. This process, called nuclear fusion, is the quiet miracle that keeps the universe alight. Each time two hydrogen nuclei fuse, a tiny fraction of their mass is lost and transformed into pure energy, radiating outward through the layers above. It's a simple reaction, but multiplied by countless trillions of times every second, it produces all the light and warmth a star will ever give. For the first time, the inward pull of gravity is perfectly matched by the outward push of energy from the core. This is the moment when a star becomes truly alive. Gravity still presses inward, trying to crush the sphere tighter, but radiation and heat flow outward in equal measure, holding everything in delicate balance. The star no longer contracts, it no longer swells. It breathes evenly, stable and serene. It has entered what astronomers call the main sequence, the longest and most peaceful stage of a star's existence. From the outside, a main sequence star appears calm, but inside, it is a place of relentless activity. Every second, an enormous number of hydrogen atoms collide and fuse, releasing energy that slowly travels outward through dense layers of plasma. The journey from the core to the surface can take hundreds of thousands of years, as photons bounce and scatter countless times before finally escaping into space. Once they do, the light races outward at full speed, illuminating worlds and warming distant planets. In the main sequence, mass determines destiny. A star's weight decides its temperature, colour, brightness, and lifespan. The smallest stars, known as red dwarfs, burn through their hydrogen with extreme thrift. They glow dimly, but their fuel lasts for trillions of years, longer than the universe has existed so far. In contrast, the most massive stars are astonishingly bright but spectacularly short-lived. They burn through their fuel hundreds of thousands of times faster, living only a few million years before they collapse and die. It's the cosmic version of burning the candle at both ends, brilliant but brief. Our Sun, sitting comfortably in the middle of this stellar spectrum, offers a good example of steady moderation. It's neither the faintest nor the most dazzling, but it is extraordinarily stable. For over 4.5 billion years it has provided nearly constant warmth and light to the solar system, its energy output varying by only a tiny fraction. Its yellow-white glow is a sign of balance, not too hot, not too cool, perfectly suited to sustain the worlds that orbit it. Inside the Sun, the core is a furnace with temperatures reaching around 15 million degrees Celsius. Hydrogen atoms collide so violently that they overcome their natural repulsion and fuse into helium. Each fusion event produces energy that keeps the star from collapsing under its own weight. The energy travels outward first by radiation, photons bouncing through the dense plasma, and later by convection, where massive bubbles of hot gas rise and cool gas sinks in great slow currents. Finally, at the surface, that energy escapes as sunlight, a soft golden beam that has travelled through unimaginable resistance just to reach open space. Despite the violence of its internal reactions, the sun's surface is a picture of calm when viewed from afar. Its light flickers only slightly, and even solar storms, impressive though they are, barely change its overall brightness. If the sun were a candle, it would be the steadiest flame ever lit, burning quietly without a tremor for billions of years. Every main sequence star finds this same balance, each one a different version of the same cosmic compromise. The hotter, heavier stars glow blue-white and emit tremendous energy, their surfaces blazing at tens of thousands of degrees. The cooler, smaller stars are reddish and faint, glowing at just a few thousand degrees, but regardless of their colour, all main sequence stars are in the same delicate equilibrium, suspended between collapse and explosion, quietly turning hydrogen into helium and light. It's worth pausing to consider the timescales involved. The Sun, for instance, will spend roughly 10 billion years on the main sequence. That means it's only about halfway through its life right now. A perfectly stable middle-aged star. In contrast, a star 10 times heavier might live only 10 million years before it burns out, while a tiny red dwarf might endure for more than 10 trillion years. The smallest ones in the universe today have not even had time to age since the dawn of creation. They will still be shining when galaxies themselves begin to fade. From a human perspective, a star's stability is almost inconceivable. Civilizations rise and fall, species appear and vanish, entire mountain ranges erode to dust, all while the same stars continue shining, unbothered by time. A main sequence star is patience made visible, a reminder that the universe's rhythm is far slower than our own. If you could somehow float near one of these suns, you wouldn't see the frenzy of fusion inside, only a calm, luminous sphere. The surface would shimmer faintly with granules of rising and falling gas, each one the size of a continent. The sound, if it could travel through space, would be a deep, resonant hum, the slow heartbeat of energy being born. Every photon that escapes carries with it the story of atomic struggle, a journey from the dense heart of matter to the open sky. And scattered across the galaxy, billions upon billions of stars are doing exactly the same thing. Each one, from the faintest ember to the most blazing giant, maintains its delicate harmony for as long as its fuel allows. It's this vast population of main sequence stars that gives galaxies their familiar glow, that defines the constellations, and that sets the stage for everything else that happens in the universe. In the grand cosmic sense, this phase of a star's life is its moment of peace. After the turbulence of formation, and before the chaos of death, a main sequence star simply shines, not struggling, not changing, just existing. It is the universe's purest expression of balance, a self-sustaining flame that burns without consuming itself. For billions of years, a star like the Sun will rise and set over its worlds, indifferent to time yet essential to everything that depends on its light. If the night sky feels calm, it's because most of the stars we see are in this tranquil stage, silent furnaces, each holding its own steady conversation between gravity and light. They remind us that even in a universe driven by change, there are moments, or rather epochs, of perfect stillness. A star in balance is like a candle that never flickers, its flame unbroken across the ages, whispering that peace, too, can be powerful. When you look up at the night sky, it might seem as though every star is just a pinprick of white light. But look a little closer, or rather, let a telescope do the looking for you. And those tiny points of light reveal an entire spectrum of secrets. Stars aren't all white at all. Some gleam a deep red, others a rich orange or golden yellow, and the hottest among them blaze with blue or even blue-white intensity. Those colours are more than decoration. They are clues. A star's colour tells you its temperature. It's the same principle that makes metal glow red when heated and white when it becomes unbearably hot. The cooler stars at only a few thousand degrees shine with a reddish hue. The Sun, sitting at a comfortable middle temperature of around 5,500 degrees Celsius, glows with a soft yellow-white, and the hottest stars, those 10 times heavier than our Sun, reach temperatures of 30,000 degrees or more, radiating with a brilliant icy blue light. It's a curious irony. The bluer the colour, the hotter the star. If you ever see a star shimmering with a pale sapphire glow, you're looking at one of the universe's true overachievers. But astronomers don't stop at colour. They go deeper, breaking starlight apart to see what it's really made of. When light passes through a prism or a diffraction grating, it spreads into a rainbow, a spectrum. In that rainbow, certain dark lines appear, thin and sharp, where specific wavelengths of light are missing. These are absorption lines, and they're caused by elements in the star's outer layers absorbing particular colours of light as it escapes. Each element, hydrogen, helium, calcium, sodium, iron, leaves its own distinct pattern of lines, a bit like a barcode or a fingerprint. By comparing those patterns to what we see in laboratories on Earth, astronomers can tell exactly which elements are present in a star, even if it's hundreds of light years away. It's an astonishing feat when you think about it, determining the chemical makeup of something you can never touch, just by studying the light it sends you. Through spectroscopy, we've learned that stars are mostly hydrogen and helium, but with traces of heavier elements, the same ones that make up planets, oceans, and people. In a way, reading a spectrum is like reading the autobiography of a star, written in the language of light. The spacing of those lines, too, can tell us how a star is moving. If the lines are shifted slightly toward the red end of the spectrum, the star is moving away from us, a red shift. If they're shifted toward blue, it's moving closer, a blue shift. This simple observation allows astronomers to measure motion across incredible distances. Entire galaxies can be seen drifting apart by watching how their light stretches as it travels through expanding space. Every twinkle in the night sky carries not just brightness, but direction, velocity, and history. All of these measurements, colour, temperature, brightness, and chemical fingerprint, come together in one of astronomy's most powerful tools, the Hertzsprung-Russell diagram. It might sound intimidating, but it's really just a kind of map, a chart that shows where stars fall according to their brightness and their colour, or temperature. When astronomers plot thousands of stars on this diagram, a clear pattern emerges. Most stars line up along a broad diagonal band. That's the main sequence, the long middle phase of stellar life when hydrogen fusion keeps them stable. Above it, a scattering of bright, cooler stars marks the giant and supergiant stages, while below lie the tiny faint white dwarfs, the relics of stars long gone. The Hertzsprung-Russell diagram is like a family portrait of the stars. By seeing where a star sits on the chart, you can tell what stage of life it's in, how hot it burns, and how long it's likely to survive. Astronomers can even predict how a star will change with time, whether it will swell into a red giant, explode as a supernova, or quietly fade away. the diagram turns what would otherwise be a sky full of random lights into a coherent story of birth, life, and transformation. But to place a star on that chart, we need to know not just how bright it looks from Earth, but how bright it truly is. The difference between apparent brightness and intrinsic brightness can be enormous. A small nearby star might appear dazzling, while a truly gigantic one at great distance could look faint. So how do we tell how far away they are? For the closest stars, astronomers use a beautifully simple technique called parallax. Imagine holding your finger out in front of you and looking at it first with one eye, then the other. You'll notice your finger seems to shift position against the background. That tiny change is parallax, the same effect astronomers use but on a cosmic scale. As Earth orbits the Sun, nearby stars appear to shift slightly against the backdrop of more distant ones. Measuring that shift allows us to calculate their distance with precision. The angles are unbelievably small, often less than 1,000th of a degree, but modern telescopes can detect them with ease. For stars too distant for parallax to work, astronomers use light itself as the measuring stick. Certain types of stars, like Cepheid variables, brighten and dim in a regular rhythm. The period of their pulsation reveals their true luminosity, and by comparing that with how bright they appear, we can estimate their distance. This discovery, made early in the 20th century, allowed us to measure not just nearby stars, but entire galaxies. It's no exaggeration to say that this rhythmic flicker in a few distant suns helped us realize the vast scale of the universe. Today, satellites such as Gaia are mapping the positions and motions of over 1 billion stars, turning our vague picture of the Milky Way into a detailed 3-dimensional map. From those data, astronomers can trace spiral arms, measure the Sun's orbit around the galactic center, and even predict the slow drift of stars millions of years into the future. Every speck of light in the sky becomes a coordinate, a clue to how our galaxy breathes and moves. When you add it all together, color, spectra, distance, and brightness, you get an incredibly detailed understanding of stars, all without ever visiting one. It's a kind of cosmic detective work, patient and precise. Astronomers have to interpret the smallest hints, a fraction of a wavelength here, a shift in brightness there, to reconstruct what's happening light years away. It's as if they're reading ancient scrolls written in a fading language of photons, deciphering secrets from long before humanity even existed. In that sense, astronomers really are the librarians of the cosmos, hunched over their shelves of starlight, cataloguing every flicker and hue. Each new observation adds another page to the universe's grand archive. And the more we read, the more we realize that the stars are not distant strangers, but familiar storytellers, whispering their physics across the dark. So the next time you look up and see a star twinkling faintly above, remember, that tiny glimmer carries its temperature, its chemistry, its distance, and even its motion, all woven into a single beam of light. What looks like a speck is, in truth, a detailed message, a postcard from the heart of a sun, delivered across space and time, waiting for someone patient enough to read it. In the grand census of the galaxy, the stars that dominate are not the bright, showy giants that catch our eye, but the faint, humble red dwarfs. They are the quiet workers of the cosmos, small, cool and steady, yet far more numerous than all other kinds of stars combined. If our eyes could see the universe as it truly is, the Milky Way would not shimmer with white and blue light, but with a soft red haze. Red dwarfs are the galaxy's quiet heartbeat, burning dimly and patiently in every corner of space, A typical red dwarf contains less than half the mass of our Sun, and some are barely 8% of its size, just heavy enough to spark hydrogen fusion at all. Any smaller, and gravity cannot squeeze the gas tightly enough to ignite the reactions that define a true star. Because of their low mass, red dwarfs are also cool by stellar standards, with surface temperatures between 2000 and 4000 degrees Celsius. That's enough to glow, but not to dazzle. Their light is a deep red, sometimes with hints of orange or magenta, more ember than flame. Their faintness makes them difficult to spot with the naked eye. Out of all the bright stars you can see on a clear night, not one is a red dwarf, even though they make up roughly 3/4 of all stars in our galaxy. They hide in plain sight, everywhere, yet rarely seen. Our nearest neighbour, Proxima Centauri, is one such star. It lies just over 4 light-years away, closer than any other sun, yet it's so faint that you need a telescope to see it. Were it to replace the sun in our sky, daylight would never come. Earth would remain in a dim twilight under a pale crimson glow. The secret to a red dwarf's extraordinary longevity lies in how it burns its fuel. The fusion reactions inside these stars proceed at a leisurely pace, converting hydrogen into helium with remarkable efficiency. Their internal structure helps as well. Unlike stars like the Sun, which have distinct core and surface layers, red dwarfs are fully convective. That means their material mixes constantly from the centre to the outermost regions, circulating heat and fresh hydrogen throughout. No part of the star is left untouched, and none of its fuel goes to waste. As a result, a red dwarf can burn nearly all its hydrogen before fading, a slow, even consumption that stretches its life far beyond any other kind of star. The smallest red dwarfs may live for 10 trillion years or more, which is roughly 1,000 times the current age of the universe. That's so long that none have yet reached the end of their lives. The universe simply hasn't existed long enough for a single red dwarf to die of old age. Everyone ever born is still burning today, quietly, steadily, as it has since its formation. Somewhere in the far future, when the larger stars are gone and the galaxies grow dim, these tiny suns will still be shining, a long, slow afterglow of cosmic persistence. Their faint light, though gentle, can also be unpredictable. Many red dwarfs produce powerful flares, bursts of radiation, and charged particles released when their magnetic fields twist and snap. These flares can briefly make a star hundreds of times brighter, lighting up its surroundings with an intensity far beyond its usual calm. To a planet nearby, such an outburst could strip away atmospheres or bathe its surface in energetic particles. Astronomers have observed some red dwarfs flaring several times in a single day, their otherwise quiet faces erupting with sudden energy. It's as if these stars, despite their patience, occasionally lose their temper. Yet even these flares don't truly break their composure. After each storm, the light settles back into its steady red glow. In the long run, red dwarfs remain the definition of stability. They sip fuel instead of devouring it, drift through their orbits without fuss, and survive when all others have burned out. To imagine one is to picture a cosmic ember, not dazzling, not loud, but unwavering through eternity. Their small size and low energy output make them fascinating when it comes to planets. Because they are so faint, any habitable zone, the region where temperatures could allow liquid water, lies much closer to the star than Earth is to the Sun. A planet in that zone might orbit its star in only a few days, so close that one side always faces the star while the other remains in perpetual night. On the bright side, That closeness makes such planets easier to detect, since their tight orbits cause noticeable wobbles in the star's motion or tiny dips in brightness as they pass in front. In fact, many of the exoplanets discovered so far, including some potentially rocky Earth-sized worlds, orbit red dwarfs. However, life around such stars would face unique challenges. The frequent flares could be harmful, and the dim red light might make photosynthesis less efficient. Still, the sheer abundance of red dwarfs means that if life can adapt to these conditions, the universe could be teeming with it. Statistically speaking, most of the planets in the galaxy probably orbit stars like these. It's even possible that most living things, if they exist elsewhere, do so under red light rather than yellow. Over time, red dwarfs change very little. They slowly brighten and warm as helium builds up in their cores, but their evolution is so gradual that even after billions of years, the difference is barely noticeable. Eventually, after trillions of years, they'll exhaust their hydrogen, fading gently into cool, dense remnants called white dwarfs. But that chapter of cosmic history lies unimaginably far in the future, long after our own Sun and Earth are gone, long after the Milky Way has merged with its neighbouring galaxies, and perhaps long after life itself has vanished from the universe. For now, red dwarfs remain the quiet companions of the cosmos, dim but enduring, unassuming but essential. Their slow-burning hearts will keep the night faintly lit long after the brighter stars have faded. Theirs is not a story of spectacle but of endurance. If you could float among them, drifting through the galaxy's outskirts where they cluster like embers in the dark, you'd see a calm scene. Tiny red glows scattered across the void, each one steady and self-contained. No flicker, no grand display, just a soft persistence of light. In a universe that rushes toward change, red dwarfs remind us that sometimes the smallest fires burn the longest. This sun, for all its warmth and steadiness, is not eternal. Like every star, it lives by a balance between gravity pulling inward and fusion pushing outward. That balance depends on the steady conversion of hydrogen into helium deep within its core, a quiet, continuous rhythm that has lasted for more than 4 billion years. But eventually even the most reliable flame runs low on fuel. When the sun's core hydrogen begins to dwindle, a slow transformation will begin, one so gradual that no single generation of life would ever notice it happening. Yet over cosmic time, it will change everything. As the supply of hydrogen in the centre runs thin, the fusion that once held gravity at bay starts to falter. Without that internal pressure, the core begins to shrink under its own weight, compressing the leftover helium into an ever denser ball. As it contracts, it heats up, reaching temperatures far higher than during its youth. Around the core, a thin shell of hydrogen still remains, and it begins to burn furiously, generating more energy than ever before. But instead of stabilizing the sun, this energy flows outward into the surrounding layers, causing them to expand. The outer envelope swells and cools, transforming the once yellow star into a vast ruddy sphere, a red giant. This change won't be sudden or explosive. It will take hundreds of millions of years to unfold as the sun's surface grows hundreds of times larger than it is today. The colour will deepen to orange, then red, as the temperature at the surface drops. Paradoxically, though the sun will cool on the outside, it will shine far brighter overall, thousands of times more luminous than its familiar self. Its light will redden and soften, filling the sky of its planets with a strange, warm glow, unlike anything they've seen before. For Earth, this will not be a gentle event. Long before the sun becomes a true giant, its increasing brightness will heat our planet's surface, beyond what oceans or atmosphere can handle. Seas will boil away, clouds will vanish, and the crust will dry and crack under relentless sunlight. In the final stages, the swelling star may even reach Earth's orbit, engulfing it entirely. The innermost planets, Mercury, Venus, and likely Earth, will be lost to that fiery embrace, their matter absorbed into the outer layers of the aging sun. Mars and the outer worlds may drift outward as the sun loses mass, surviving the ordeal but in a transformed system. Yet from a cosmic perspective, there is something graceful about this transformation. Stars do not grow old with violence but with elegance. The expansion into a red giant is like a slow exhale after a lifetime of steady breathing, a release of energy that had been locked away for eons, and while it may be the end for the inner planets, it's far from the end for the star itself. Within that contracting core, something new is about to happen. The sun's central temperature will continue to rise until it reaches roughly 100 million degrees Celsius. At that point, the helium that has been quietly accumulating in the core will finally ignite. In stars like the Sun, the ignition happens suddenly, in what astronomers call the helium flash. Not an explosion in the usual sense, but a rapid onset of fusion as helium nuclei begin fusing into carbon and oxygen. These elements, forged in the intense heat of the dying core, are the raw materials that will one day become the building blocks of planets, rocks, and living things in future generations of stars. Once helium fusion begins, the sun will settle into a new, though shorter, phase of stability. The core will expand slightly and cool, while the outer layers contract a little, causing the sun to shrink somewhat from its maximum size. For a time it will burn helium quietly, turning it into heavier elements and shining with a steady brilliance. It will be, in its own way, middle-aged again. But this second calm will last only a fraction of the time the main sequence did. Within a few 100 million years, the helium too will be exhausted. The red giant phase will be the sun's most dramatic and perhaps most beautiful era. Its diameter may stretch beyond the orbit of Mercury and nearly reach that of Earth. From the outer planets, the view will be extraordinary, a crimson sun filling half the sky, casting long, soft shadows across icy moons. The solar wind will intensify, blowing streams of gas and dust into space, forming an enormous halo of glowing material. The sun will lose a significant portion of its mass this way, enriching the surrounding space with the very elements it created in its core. For astronomers observing from a safe distance, perhaps from another star system, the sun would appear as a deep red beacon, pulsating slowly as it sheds its layers. Each pulse would send more material into the cosmos, forming clouds of dust and gas that might one day gather again into new stars. This cycle of creation continues, one generation giving rise to the next. Even as it transforms, the sun will never truly lose its grace. The changes occur over millions of years, slow enough that to any witness they would seem motionless. If the sun could be thought of as a living thing, this would be its final act of generosity, returning its material to the galaxy so it can be reused. The carbon and oxygen formed inside will one day find their way into new solar systems, into planets, and perhaps even into life again. Eventually, as helium runs out and fusion finally ceases in the core, gravity will tighten its hold once more. The sun's outer layers, now weakly bound, will drift away into space, leaving behind a hot, compact core that will cool for billions of years. But that story lies beyond the red giant years, beyond the phase where the sun's light glows soft and ruddy, casting one last warmth across the remains of its ancient family of worlds. When you look up at the sun today, shining steadily in its prime, it can be hard to imagine such a distant future. But this long, graceful aging is the natural fate of all stars like it. They don't rage against time, they expand, soften, and share their light more generously than ever before. And though the red giant sun will mark the end of our world, it will also be an artist at the height of its power, painting the sky in glowing reds and golds, sculpting new clouds of creation, and proving that even in its final chapters, a star can age beautifully. When a star like the sun nears the end of its red giant life, it doesn't collapse in a violent explosion or vanish quietly into darkness. Instead, it leaves the stage in an act of astonishing grace. The outer layers that once made up the star's surface begin to drift away, peeling off into space in delicate waves. The process is slow and rhythmic, like breathing. Each pulse of the dying star sends another thin veil of gas outward, expanding and cooling as it goes. These layers spread out to form vast translucent shells of gas, glowing softly against the black canvas of space. This is the star's gentle farewell, a planetary nebula, a name that, despite how it sounds, has nothing to do with planets. The term planetary nebula is a historical accident. When early astronomers peered through small telescopes in the 18th and 19th centuries, they saw these faint round clouds surrounding tiny bright centres. The shapes reminded them of distant worlds, small disks like Uranus or Neptune, and so they called them planetary. Only later did scientists realize that these objects were not planets at all, but the remnants of dying stars, the final exhalations of suns much like our own. The name stuck, a linguistic fossil from the early days of exploration, carried forward long after its meaning had changed. As the red giant's outer layers drift outward, the core left behind begins to shine fiercely. No longer fueled by fusion, it's now a dense ball of carbon and oxygen, still glowing from the tremendous heat it retains. This exposed core radiates intense ultraviolet light, invisible to the eye but powerful enough to ionize the surrounding gas. When that ultraviolet light strikes the expanding cloud, it excites the atoms within, causing them to emit visible colors: emerald greens from oxygen, reds from hydrogen, and blues from helium. Together, they create some of the most beautiful and ethereal shapes in the universe. Seen through telescopes, planetary nebulae come in astonishing variety. Some are nearly spherical, like delicate soap bubbles adrift in the dark. Others are elongated, hourglass-shaped, or even butterfly-like, with twin lobes of gas stretching in opposite directions. These intricate forms are shaped by the star's magnetic fields, by the slow spin of the core, and sometimes by the gravitational influence of unseen companion stars. The symmetry of their shapes is mesmerizing. Art sculpted by physics, painted in light. What we're witnessing in these nebulae is a moment of transformation. The gas and dust that once belonged to a single star are being returned to the galaxy. Within a few tens of thousands of years, a blink in astronomical terms, the nebula will spread out and fade, mixing with interstellar space. But while it lasts, it is breathtaking, a cosmic chrysalis, glowing with the last light of its parent star. The atoms drifting outward will one day find their way into new clouds, new stars, new planets. In that sense, death and creation are inseparable. The core that remains, now a white dwarf, is one of the most extreme objects in existence. Roughly the size of Earth, it contains about half the Sun's mass, packed so tightly that a teaspoon of its material would weigh tons. It shines not because it's generating new energy, but because it's still hot, incredibly so, at first reaching 100,000 degrees or more. Over billions of years it will gradually cool and fade, but for now it sits at the centre of its own artwork, a brilliant white jewel surrounded by drifting colour. From that distance, it looks eternal, though it is only passing through the final quiet stage of its long life. Astronomers have catalogued thousands of these nebulae across the Milky Way. The Ring Nebula in Lyra, the Helix Nebula in Aquarius, the Cat's Eye Nebula with its hypnotic concentric shells. Each is a variation on the same theme. A star's farewell turned into a masterpiece. The patterns are not random. They reflect the symmetry of nature itself, guided by physics and time. In some, faint jets or ripples reveal how the dying star's wind sculpted its own surroundings. In others, delicate filaments trace the paths of dust grains moving through ionized gas, glowing where starlight catches them. Despite their beauty, planetary nebulae are fleeting phenomena. After about 20 or 30,000 years, the gas drifts so far from the white dwarf that it cools and fades into invisibility. Compared to the billions of years a star spends alive, this stage is over in a heartbeat. Yet for that brief time, the dying star becomes something more spectacular than it ever was in life. A luminous sculpture, a final gesture of generosity to the cosmos. From a great distance, a planetary nebula would be almost invisible to the human eye, too faint for even the sharpest vision. But if you could see it up close, the view would be unforgettable. The colours wouldn't appear as the bold blues and reds captured in photographs. Those are often enhanced to reveal details, but as a faint misty glow, like gauze illuminated by candlelight. The gas moves outward at tens of kilometres per second, yet because space is so vast, it seems frozen, as if time itself had slowed to watch the moment unfold. These nebulae also play an essential role in cosmic recycling. The material they return to space enriches the interstellar medium with carbon, nitrogen and oxygen, elements that form the foundations of life. Without countless stars undergoing this process before the sun was born, Earth could never have existed. Every breath you take, every cell in your body carries atoms that once belonged to ancient stars that died this way. The universe, it seems, has a talent for reusing its materials beautifully. There's something deeply peaceful about the thought of a planetary nebula. It's not destruction, not an ending in the usual sense, but a transformation, a final act of sharing. The star, having spent its lifetime generating light, now releases its very substance into space, creating patterns that will drift for millions of years. In its quiet, colourful death, it adds one last piece to the grand tapestry of the cosmos. When we look at these glowing clouds through our telescopes, we're not just seeing the aftermath of stellar aging, we're witnessing the poetry of physics, energy made visible, structure born from symmetry, beauty rising from inevitability. The name planetary nebula may be a misnomer, but it carries a quiet charm, a reminder that even in misunderstanding, humanity found wonder in what it saw. So picture it, a dying star, no longer blazing with youthful energy, exhaling its final layers into the dark. Its ultraviolet breath paints the surrounding gas in blues and greens and crimson swirls. At the centre, a small white ember continues to glow, steady and calm. The star's long journey has ended not with silence, but with art. A cosmic self-portrait, drifting slowly into eternity. When the final shells of gas drift away and the glowing nebula fades into darkness, what remains of a once mighty star is something small, compact, and quietly enduring: a white dwarf. From a distance it might look like a faint pale pinprick of light, almost unremarkable. But this tiny object is one of the strangest forms of matter in the universe, a leftover core that has defied collapse and continues to shine, not through fusion or fire, but through the stubborn heat trapped within. A white dwarf is the exposed heart of a dead star, the dense remnant left behind after a red giant has cast off its outer layers. Although it may be no larger than Earth, it contains roughly half the mass of the Sun. The matter inside is so compressed that a single teaspoon of it would weigh several tons. Gravity has crushed the atoms so tightly that the electrons no longer orbit their nuclei freely. Instead, they form a degenerate gas, a quantum sea that resists further compression. It is this strange pressure, born from the rules of quantum mechanics, that keeps a white dwarf stable. The electrons themselves, crowded together, simply refuse to occupy the same space. There is no fusion taking place inside a white dwarf. Its days of producing energy are over. The light it emits comes from the heat remaining from its former life, the residual warmth of a core that once burned at unimaginable temperatures. When first exposed, a white dwarf can be hundreds of thousands of degrees hot, but with no new fuel, it begins to cool. Slowly, patiently, over billions of years, it radiates that stored heat into space, dimming bit by bit. The cooling is so gradual that many white dwarfs in our galaxy, though ancient, still shine faintly today. None have yet gone completely dark. The universe simply isn't old enough for that. At first glance, a white dwarf might seem like an ending, a leftover husk with no future, but in truth, it is a triumph of balance. Gravity and quantum pressure in perfect opposition, each keeping the other in check. If it were slightly heavier, gravity would win, and the star would collapse further, becoming a neutron star or even a black hole. But within a certain mass limit named after physicist Subrahmanyan Chandrasekhar, the electron's resistance is strong enough to halt the collapse entirely. The result is an object that neither expands nor shrinks, neither burns nor freezes quickly, existing in a state of quiet permanence. Over time, as the white dwarf cools, something remarkable happens deep within. The atoms begin to settle into an ordered structure, a crystal lattice, similar to the way water freezes into ice, but on a cosmic scale. The entire star slowly crystallizes from the inside out, transforming into an enormous gemstone of carbon and oxygen. Astronomers have even detected signs of this process in nearby white dwarfs, suggesting that some have already become colossal diamonds adrift in space. If the Sun one day ends its life this way, then billions of years from now, its core could harden into a glittering sphere the size of Earth, a literal diamond star hidden in the night. As centuries turn to millennia and millennia to eons, the cooling continues. The white dwarf grows fainter and redder, slipping into near invisibility. After perhaps 100 billion years or more, it will become what astronomers call a black dwarf, an object so cold it emits no light at all, its energy spent, its surface as dark as the surrounding space. But that phase lies far beyond our present era. The universe itself is only about 13 billion years old, far too young for a single black dwarf to yet exist. For now, all white dwarfs still carry a lingering glow, the ghostly afterlight of stars long dead. Despite their silence, white dwarfs remain vital players in the cosmos. Many exist in binary systems, orbiting alongside still living stars. In some cases, they draw matter from their companions, triggering bursts of renewed brilliance. A sudden inflow of gas can ignite fusion on the surface, producing a nova, a brief but spectacular brightening that reminds us that even in apparent death, a star can still find ways to shine again. These interactions help shape galaxies, enrich space with heavier elements, and sometimes lead to the grand explosions known as Type 1a supernovae, which serve as cosmic beacons for measuring the scale of the universe. Yet most white dwarfs live quiet, solitary lives. They drift through the galaxy like cosmic embers, slowly fading but never truly extinguished. Their light may be faint, but it's remarkably steady. No flares, no sudden outbursts, no tremors of instability. They simply exist, perfect in their simplicity, marking the end of a stellar story with calm dignity. Some move through interstellar space entirely alone, their parent systems long gone, shining to no audience but the stars themselves. Others travel in small clusters, remnants of ancient generations of suns, each carrying within it the record of how bright the universe once was. If you could stand on the surface of a white dwarf, assuming you could somehow survive its crushing gravity, the view would be surreal. The sky would curve around you under intense gravitational lensing, bending starlight like ripples around a pebble. A single step would be impossible. Your weight would be multiplied hundreds of thousands of times. The heat beneath your feet would be immense, yet the star would appear still, motionless, silent. Time itself would seem to slow in the grip of such gravity. Even in decay, a white dwarf is a monument to endurance, the final immovable memory of a once luminous life. Eventually, over unthinkable spans of time, the faint heat will fade, the crystal lattice will cool, the last photons will escape, and the star will slip beneath the threshold of detectability. It will not disappear, but it will no longer shine. A black dwarf will remain, a cold, solid relic adrift in eternal night. No one will see it, no one will feel its warmth, yet it will still exist, the silent echo of what once was. There's something quietly poetic in this ending. After a lifetime of radiance, a star does not explode or vanish, it simply settles into peace. Its energy spent, it becomes an object defined by stillness rather than motion, by structure rather than light, and yet in that stillness it keeps its essence, the matter it forged, the story it wrote in light. The atoms that once made worlds and warmed skies remain bound together, waiting for whatever future the universe still holds. The white dwarf is the final heartbeat of a star, a testament to balance and endurance. It reminds us that even as energy fades and brightness dims, the legacy of what once burned fiercely can linger for ages beyond comprehension. Even when a star has stopped shining, its quiet glow continues to speak, a whisper across eternity, carrying the faint memory of light. Despite what the night sky might suggest, most stars are not solitary wanderers. They prefer company. More than half of all stars in the galaxy are part of binary systems, pairs locked together by gravity, circling a shared center of mass in endless cosmic partnership. Some pairs are nearly twins, born together from the same collapsing cloud, while others differ dramatically in size, brightness, and temperament. The result is an astonishing variety of relationships, some harmonious, others tempestuous, and a few downright catastrophic. A binary system can look deceptively calm from afar, two small points of light orbiting each other like dancers in slow motion. But up close, this story is far more intricate. Gravity binds them together, but it's also a mischievous force, capable of stirring drama on scales that defy imagination. If the stars are far apart, they live peaceful lives, barely influencing one another. Yet when they orbit close together, their gravitational pull begins to distort their shapes, drawing each into an elongated form that points toward the other. Astronomers describe this as filling one's Roche lobe, a region of space where a star's gravity dominates. When a star grows large enough to exceed this boundary, gas begins to flow toward its companion, creating a bridge of material between them. This flow of matter, called mass transfer, is where binary life gets interesting and occasionally messy. Imagine one star swelling into a red giant, its outer layers brushing the gravitational edge of its partner. Instead of staying put, that gas begins to spill over, spiraling around the smaller star in a glowing disk of plasma. As the gas falls inward, it releases enormous amounts of energy, heating to millions of degrees and radiating in ultraviolet and X-rays. From a safe distance, such a system would look like a brilliant flickering beacon, the result of one star quite literally feeding the other. It's the universe's version of a complicated relationship, one partner giving a bit too much, the other taking perhaps more than it should. Not all transfers are gentle. If the flow becomes unstable, it can lead to violent outbursts, sudden flares of light that astronomers call novae. In these events, a white dwarf accretes hydrogen from its companion until enough collects on its surface to ignite in a brief but explosive burst of fusion. The explosion doesn't destroy the white dwarf, it simply blows off the outer layer, shining thousands of times brighter for a short period before fading again. Some systems repeat this process in cycles, erupting every few decades like fireworks in slow motion. But sometimes the balance tips too far. If the white dwarf keeps gathering mass without relief, it can eventually exceed its upper stability limit, and at that point, gravity wins. The star collapses inward and then detonates in a catastrophic thermonuclear explosion, a type 1 supernova. In an instant, the entire star is obliterated, releasing more energy than the Sun will produce over its entire 10 billion year lifespan. These explosions are so uniformly bright that astronomers use them to measure the distances to distant galaxies, turning stellar drama into one of the most valuable tools in cosmology. Other binaries evolve differently. If both stars are massive, they may each live fast and die young, collapsing into neutron stars or black holes. Sometimes the remnants stay together, continuing their dance as invisible partners. As they orbit, they lose energy through gravitational waves, ripples in the fabric of space-time itself. Over millions of years, their orbits shrink until finally they merge in a spectacular burst that sends those waves racing across the cosmos. Telescopes on Earth have detected these events, confirming Einstein's century-old prediction that even gravity can make soundless music. For less extreme pairs, life can be surprisingly stable. Some binaries are wide enough that the stars evolve almost as if they were alone, though they still influence each other through subtle gravitational tugs. Others share material more evenly, exchanging gas back and forth in a gentle rhythm. In a few cases, the two stars are so close that their outer layers touch, forming what's called a contact binary. Two stars merged at the surface but still with separate cores. From a distance they appear as one, pulsing in brightness as they orbit, like a slow heartbeat of light. It's the celestial equivalent of finishing each other's sentences. There are even triplets and quadruple systems, where multiple stars orbit in intricate hierarchies. The gravitational geometry becomes complex and often unstable, leading to slow orbital exchanges or even ejections. One star might be flung away entirely, leaving the others bound more tightly. In this sense, stellar families behave not unlike human ones, dynamic, unpredictable, and prone to the occasional dramatic separation. Binary interactions also create some of the most visually stunning objects in the galaxy. Many planetary nebulae owe their strange hourglass or butterfly shapes to hidden companions influencing the dying star's final outflow. The sculpted symmetry, the jets, and the spiral arcs seen in these nebulae are the handiwork of gravitational cooperation, one star shaping the death throes of another. What we perceive as beauty in space is often the byproduct of cosmic choreography. Even stars that end their lives as black holes can continue their partnership. A black hole and a normal star can form what's known as an X-ray binary. In such systems, the black hole's immense gravity draws gas from the companion, heating it to extraordinary temperatures as it spirals inward. The result is an intense X-ray glow, a telltale sign of matter on the edge of oblivion. It's a relationship in which one partner literally consumes the other, a bit grim perhaps, but endlessly fascinating. For astronomers, binaries are a gift. By studying their orbits, we can measure stellar masses precisely, something impossible to do for single stars. The shifting of their spectral lines, the timing of eclipses, and the rhythm of their brightness variations all reveal information about their structure, size, and evolution. In a sense, binary stars are nature's laboratories, allowing us to test the physics of light, gravity, and matter under conditions no experiment on Earth could ever reproduce. There's also a quiet poetry to the idea of stars living their lives in pairs. They're born together, grow together, and in many cases die together. Some nurture one another, sharing warmth and material in harmony. Others clash, pulling each other apart through gravity's relentless grip. But even in chaos, there's a kind of order, the intricate geometry of two bodies locked in motion, each shaping the other's fate. If you could watch them from afar, you might think of them as cosmic dancers, two lights moving in perfect synchrony, turning endlessly in the dark. Sometimes their orbits tighten until they merge into one. Sometimes they drift apart, never to meet again. And every now and then, one partner's change sparks transformation in the other. A sudden brightening, a collapse, a rebirth. It's a reminder that in the vast loneliness of space, even stars are drawn to companionship, for better or for worse. Astronomers like to joke that binary systems are proof that the universe enjoys a bit of drama. Some stars are nurturing, quietly supporting their companions for billions of years, while others are fiery and impulsive, ready to consume or explode at the slightest disturbance. But whatever their temperament, binaries give the galaxy its variety and texture. They are the cosmic storytellers, weaving together tales of attraction, loss, and renewal. And through their endless dance, they show that even in the coldest reaches of space, gravity still knows how to keep things interesting. Among all the ways a star can die, few are as precise, dramatic, and useful as the explosion of a white dwarf in what astronomers call a Type Ia supernova. These are not chaotic blasts of random violence, but perfectly calibrated cosmic events, repeating the same astonishing display over and over across the universe. Each one releases nearly the same amount of light, making them invaluable to science. And yet, at their core, they are still acts of destruction. A quiet, dense remnant, long thought to be at peace, suddenly finds itself pushed beyond its limits. When that happens, it does the only thing a white dwarf can do. It goes out in a blaze of impossible brightness. The story begins with companionship. Many white dwarfs orbit other stars, remnants paired with still-living companions. The balance between them can persist for billions of years, but when one star swells, perhaps becoming a red giant, some of its gas begins to drift across the gravitational divide. The white dwarf, ever the quiet collector, pulls this material in, slowly adding to its mass. For a time, this feeding may cause small outbursts, brief novae where hydrogen ignites on the surface. But as the process continues, something more dangerous begins to happen deep within. A white dwarf is held up not by heat or pressure from fusion, but by quantum mechanics itself, by the refusal of electrons to be squeezed into the same space. This resistance, called degeneracy pressure, is incredibly strong, but it has a limit. Once the star's mass grows beyond about 1.4 times that of the Sun, gravity wins. The electrons can no longer hold back the inward pull, and the star begins to collapse. But before it can crush itself completely, the temperature in its core climbs so sharply that the carbon and oxygen inside suddenly ignite. Unlike in normal stars, this ignition doesn't happen gradually or safely. In a white dwarf, there's no room for expansion to relieve the pressure. It's a perfect powder keg. Once fusion starts, it runs away uncontrollably, spreading through the star at incredible speed. In a matter of seconds, the entire star is engulfed in a chain reaction of nuclear burning, releasing an amount of energy that defies imagination. The result is a supernova, an explosion so luminous it can outshine an entire galaxy for a short time. The brightness of a Type 1a supernova is staggering. For a few weeks, the light it emits equals that of billions of suns combined. Even from millions of light years away, these events can be seen as brilliant new points in distant galaxies, bright enough for early astronomers to notice them centuries ago with nothing more than their eyes and simple telescopes. Today, they're observed with precision instruments that track their rise and fall in brightness, revealing just how consistent these explosions really are. That consistency is what makes them so valuable. Every Type Ia supernova follows roughly the same script, the same peak luminosity, the same fading pattern, the same color evolution over time. They're nature's standard candles, identical lanterns scattered across the universe. By comparing how bright they appear to how bright they're known to be, astronomers can measure distances with astonishing accuracy. This simple principle has reshaped our understanding of the cosmos. In the late 20th century, teams of astronomers used Type Ia supernova to measure how quickly distant galaxies were receding from us. The results were unexpected. The expansion of the universe was not slowing down, as gravity should dictate, but accelerating. Some mysterious force was pushing space itself apart. That discovery led to the idea of dark energy, a term that still sounds like something out of science fiction, but represents one of the greatest puzzles in modern physics. In a very real sense, the calm deaths of ancient white dwarfs revealed the restless future of the universe. Beyond their usefulness as cosmic yardsticks, these explosions also serve an essential chemical purpose. The tremendous energy of a Type Ia supernova forges and flings heavy elements into the interstellar medium, enriching it with iron, nickel, and other metals. Much of the iron in your blood, the metal in your tools, and the core of Earth itself was born in such detonations billions of years ago. Each supernova is not just a light in the sky, it's a factory of matter, scattering raw ingredients for planets and life. The cosmos, it seems, recycles even its catastrophes. Although all Type Ia supernovae share a common outcome, they can begin in more than one way. Some occur when a white dwarf steals gas from a normal companion, the so-called single degenerate scenario. Others happen when two white dwarfs orbit each other for eons, gradually spiraling closer as they lose energy. Eventually they merge, and the combined mass exceeds the critical limit, triggering the same explosive end. Whichever path they take, the final moment is swift and irreversible. In less than a second, the white dwarf that once shone softly as a fading ember becomes a roaring sphere of nuclear fire. After the explosion, nothing recognizable remains. The star is obliterated completely, its atoms scattered across space at thousands of kilometers per second. The expanding cloud glows for months as radioactive nickel decays into cobalt and then iron, powering the fading light we see from Earth. What starts as dazzling brilliance gradually softens into a ghostly shimmer, and eventually the remnants cool into filaments of dust and gas, the ashes of a star's final blaze. Astronomers studying these remnants can still see the fingerprints of the elements forged in the blast. The characteristic lines of iron and nickel appear in the spectra of the fading light, confirming the process at work. In galaxies near and far, these same fingerprints repeat, showing that the universe keeps using the same method time after time to enrich itself. It's both mechanical and magnificent, a cosmic tradition carried out with exquisite precision. There's something paradoxical about Type Ia supernovae. They are among the most violent events in nature, yet they are predictable enough to serve as measuring tools. Their light is both a signal of destruction and a beacon of discovery. In one instant they erase their own existence, but in doing so they illuminate the universe more clearly than almost anything else. If you could somehow witness one up close, from a safe distance far beyond its reach, you'd see a star that once glowed faintly suddenly blaze to life, brighter than all its neighbours combined. The light would build rapidly, peak in a matter of days, and then fade slowly over months, leaving behind expanding waves of gas that continue moving forever. The energy released in that moment would travel across the cosmos, perhaps reaching some distant world eons later, where curious beings might study its light and learn about a universe still growing, still changing. In the end, a Type Ia supernova is a reminder that even the smallest and most unassuming stars can have spectacular endings. A white dwarf, no larger than Earth, can unleash enough energy to be seen across the observable universe. It is the ultimate example of potential energy waiting patiently for release, a faint spark that, under the right conditions, becomes a cosmic lantern. And as astronomers watch these identical lanterns scattered across the galaxies, each one a duplicate of the others, they continue to read the distances between them, mapping the shape of the universe itself. From death comes clarity, from destruction, understanding. The stars, it turns out, are not only storytellers but also teachers, and in their final breath, they light the way forward for those who are still looking up. Some stars are born to live fast and die young, while the sun and its kin take their time, burning fuel patiently over billions of years. Massive stars blaze through their lives at a breathtaking pace. They are the heavyweights of the cosmos, stars that begin with 10, 20, even 100 times the mass of the sun. Their gravity is immense, their cores fiercely compressed, and the result is a furnace of unimaginable intensity. In these titans, fusion doesn't merely happen, it roars. From the moment of their birth, everything about these stars is amplified. Their light can be millions of times brighter than the sun's, their surfaces tens of thousands of degrees hot, and their winds strong enough to strip away entire layers of their own material. Yet this brilliance comes at a cost. The same gravitational pressure that fuels their luminosity also drives them to burn through their hydrogen stores with reckless speed. What the Sun accomplishes in 10 billion years, a massive star does in only a few million. They live in fast-forward, brief, intense, and utterly spectacular. At first, the process looks familiar. Hydrogen fuses into helium in the core just as in smaller stars, but because the temperatures are so extreme, additional fusion pathways open up, allowing heavier elements to form much sooner. As the hydrogen runs out, the core contracts and heats further, igniting helium into carbon and oxygen. Once that fuel is gone, the cycle repeats. The star begins to burn carbon into neon, then oxygen into silicon, and finally, silicon into iron. Each new stage happens faster than the last. Where hydrogen burning lasted millions of years, silicon burning might last only a few days. The star's life becomes a sequence of increasingly frantic efforts to delay the inevitable. The reason iron marks the end is simple yet profound. Fusing elements lighter than iron releases energy, but fusing iron or anything heavier consumes it. When the core fills with iron, fusion grinds to a halt. There's no more fuel left that can generate pressure to counteract gravity. For a moment, the star seems almost frozen in time, a giant structure with a silent, dying heart. The outer layers continue to burn and convect, but deep inside, the core becomes inert, dense, hot, and unsupported. It's like a magnificent engine suddenly deprived of power. Then comes the most dramatic turning point in all of stellar evolution, the collapse. With no energy to resist gravity, the core implodes in a fraction of a second, shrinking from the size of a planet to something scarcely larger than a city. The speed of this collapse is astonishing. The core's material can fall inward at a quarter the speed of light. The pressure and density become so extreme that protons and electrons merge into neutrons, releasing a flood of neutrinos, ghostly particles that race outward, carrying away energy. This is the silent moment before the storm, when all motion turns inward and an entire sun holds its breath. Then, as if rebounding from the weight of its own gravity, the star detonates. The infalling material slams into the incompressible neutron core, reversing direction in a shock wave that tears outward through the star's outer layers. In less than a heartbeat, the star that once shone steadily for millions of years unravels in a supernova, one of the most powerful events in the universe. The explosion releases more energy in a few seconds than the sun will emit over its entire lifetime. But before that release, there is stillness. The transition from stability to collapse happens in less time than it takes to blink. Yet within that moment lies the greatest contrast imaginable. From roaring fusion to absolute silence, from heat and pressure to emptiness. Even the loudest stars end in a single quiet heartbeat. In their final act, these giants do more than die. They create. The shockwave from the explosion forges new elements heavier than iron, scattering them into space. Gold, platinum, uranium, and many other heavy elements are born in these brief cataclysmic moments. The remnants expand into vast clouds of glowing gas, supernova remnants, that will one day seed new generations of stars and planets. From the chaos comes enrichment. From destruction, renewal. Every atom of calcium in your bones, every bit of iron in your blood, once belonged to a star that ended this way. The cores left behind depend on the original star's mass. If the core is roughly 1.5 times the mass of the Sun, it stabilizes as a neutron star, a city-sized sphere of ultra-dense matter spinning rapidly and shining with beams of radio waves. If the core is heavier still, even neutron pressure fails, and gravity collapses it further into a black hole. These remnants, invisible or nearly so, are the echoes of once great stars, the silent monuments to lives of brilliant excess. Astronomers have long studied these massive stars both for their beauty and their role in shaping galaxies. Their ultraviolet radiation lights up the surrounding clouds, carving out glowing nebulae where new stars are born. Their winds sculpt entire regions of space, pushing and compressing gas, influencing where future stars will form. Even before they explode, they are architects of the cosmos, shaping their environment through sheer energy output. When they finally die, they leave behind not emptiness, but a richer, more complex universe. If you could observe one of these giants up close, the sight would be mesmerizing. The star would appear enormous, perhaps 1,000 times the diameter of the Sun, yet ghostly, its surface so tenuous that a spacecraft could glide through the outer layers without encountering much resistance. Tremendous convection currents would rise and fall across its surface, each the size of a planet. The colour would depend on its temperature, blue for the hottest, red for the coolest supergiants, and if you were close enough to feel its wind, it would be like standing in the path of a hurricane made of light. These stars remind us that brilliance and brevity often go hand in hand. Their short lives are the price they pay for their grandeur. While smaller stars quietly endure for eons, massive ones live fiercely and fade quickly, burning all their fuel in a cosmic sprint. Yet their deaths are what make the universe interesting, what fill it with the ingredients for planets, oceans, and life. In their youth, they shine brighter than anything else in the galaxy. In their old age, they give that light back, scattering it across the stars to come. They are proof that even fleeting lives can have lasting consequences, that even destruction can be creative, and though their ends come swiftly, their legacy stretches through time itself. In the silence that follows a supernova, the universe reclaims its breath. The dust and debris drift outward, cooling, spreading, blending with the gas between the stars. From that material, new clouds will form, and from those clouds, new stars will one day ignite. The giants may die quickly, but their story never truly ends. It just changes shape. When a massive star reaches the end of its short and furious life, it does not fade quietly. It collapses, rebounds, and erupts with a power that defies comprehension. A core collapse supernova, one of the most spectacular and transformative events in the cosmos. For millions of years, the star has fought against gravity, balancing its weight through the steady pressure of fusion in its core. But when fusion can no longer produce energy, gravity wins in an instant. The core implodes, the outer layers crash inward, and the star's final heartbeat becomes the loudest sound in the universe, though no one can hear it. The drama begins in silence. Deep inside the star, the iron core can no longer sustain fusion. Iron doesn't give off energy when fused. Instead, it consumes it. Without the steady outward push from nuclear reactions, The core collapses under its own weight, shrinking at an unimaginable pace. In less than a second, the entire center of the star, once millions of kilometers across, is compressed into an object barely 20 kilometers wide. The density skyrockets until the atoms themselves are crushed. Protons and electrons merge into neutrons, and in that violent fusion of opposites, countless ghostly particles are born, neutrinos, released in a flood that carries away most of the collapsing star's energy. At this stage, the outer layers are still falling inward, unaware that their foundation has already vanished. The collapsing core reaches a point where even neutron matter can resist no further compression, and it abruptly halts. The infalling material slams into this newly formed neutron core and rebounds outward, sending a shockwave racing through the star. The collision releases an energy so vast it's almost meaningless to measure, enough to outshine an entire galaxy for a brief time. The star, which for millions of years seemed eternal, ends its life in a fraction of a second, transformed into brilliance and motion. For a moment the shockwave falters, slowed by the dense layers it must pass through. Then the torrent of neutrinos escaping from the core gives it a final push, reigniting its power. The wave surges outward once more, tearing through the star's outer shells and blasting them into space. The energy released is staggering. In the span of a few heartbeats, the supernova radiates more power than the sun will emit in 10 billion years. To an observer light years away, it would appear as a sudden new star in the sky, bright enough to cast shadows at night. The first messengers to leave the dying star are the neutrinos. They travel unimpeded through the outer layers, racing across the cosmos long before any visible light escapes. When astronomers detected a burst of neutrinos from supernova 1987A, it was the first confirmation that this invisible flood really happens, a whisper from the heart of a collapsing star, reaching Earth before the explosion's light could even arrive. Then, hours later, the visible light breaks free, and the supernova shines in full glory, its brilliance building over days or weeks before slowly fading. What remains after the blast depends on the original star's mass. If the core was modest, it stabilizes as a neutron star, a city-sized sphere spinning rapidly and emitting beams of radiation as a pulsar. If it was larger still, gravity overwhelms even the neutrons, and the collapse continues until nothing can escape, not even light. The star becomes a black hole, the ultimate endpoint of gravity's relentless pull. But whether the result is a neutron star or a black hole, the explosion leaves behind something equally important: the gift of elements. The shockwave rips through the star's layers, fusing atoms together in its wake. In those few seconds of unimaginable heat and pressure, new elements are born: cobalt, nickel, copper, silver, and beyond. The heaviest and rarest materials in the universe come from this violent alchemy. The debris is hurled into space at millions of kilometers per hour, mixing with interstellar gas, cooling, and eventually becoming part of new molecular clouds. Those clouds, in time, will collapse again to form new stars and planets, continuing the cosmic cycle. Every atom of gold in a ring, every speck of iodine in a living cell, was once inside a dying star that ended its life this way. To the naked eye, a supernova seems like pure destruction, an obliteration of everything that came before. But to the universe, it's more like recycling on a grand scale. The old is shattered so the new can emerge. Without these colossal explosions, the cosmos would be poor in variety, limited to hydrogen and helium. There would be no planets, no oceans, no living creatures to marvel at the stars. The violence of death is what makes life possible. Supernova remnants seen through telescopes centuries after the explosion are hauntingly beautiful. The Crab Nebula, the Veil Nebula, and Cassiopeia A. Each is a tangled web of glowing filaments, expanding outward like the petals of a cosmic flower. The colours trace different elements: oxygen glowing green, hydrogen pink, sulfur red, all spreading across space. Within these filaments lies the record of creation itself, matter forged in a single moment of release. The shockwave continues to move outward, colliding with interstellar gas and lighting up the darkness like a slow-motion firework that will take tens of thousands of years to fade. Astronomers study these remnants to understand the physics behind the explosion. By tracing their structure, they can reconstruct how the shockwave moved, how energy was distributed, and how the new elements were made. Supernovae are laboratories that nature runs for free, teaching us how the universe builds itself from the inside out. The neutrinos, light and particles they send across space, are the universe's data points, each one a clue about the forces that shape matter and time. For civilizations lucky enough to witness one nearby, though not too nearby, the view would be unforgettable. A new light would appear in the sky, growing brighter night after night until it rivaled the moon. It would stay for months before dimming, eventually fading back into darkness. The idea that such brilliance could come from the death of a single star is humbling, a reminder that the universe's most beautiful sights often arise from its most violent events. And yet, for all its power, a core collapse supernova is not a final act of chaos. It's a transformation. The star's death becomes the galaxy's renewal, its ashes blending into the raw material for future worlds. The process is messy, loud, and breathtaking, but its purpose is clear. Nothing in the universe is truly wasted. Energy becomes motion, matter becomes dust, and dust becomes the seed of something new. If you could watch it all unfold from the stillness of deep space, the flash, the glow, the slow expansion, you might realize that even in destruction, there is rhythm. The star's final burst is not an ending, but a handoff, a way of giving back to the cosmos that created it. The cycle continues. Clouds collapse, stars ignite, and eventually some of them will collapse again. So when you see the faint glow of a nebula through a telescope, or look at the iron in a rock, you're seeing the quiet aftermath of a stellar farewell. The universe, for all its grandeur, is a recycler at heart, never content to let anything go to waste. Even the most brilliant explosion is, in the end, an act of generosity. When the heart of a massive star collapses, sometimes gravity stops just short of creating a black hole. Instead, it compresses the remaining matter into something equally remarkable: a neutron star. What's left behind is no larger than a city, yet heavier than the entire sun. It's the densest form of matter in the universe that can still be seen, touched in theory, and described by physics rather than mystery. A teaspoon of it would weigh billions of tons, but it's not just its weight that astonishes, it's everything about it. In a neutron star, the collapse has squeezed protons and electrons together into neutrons, forming a solid sphere of pure nuclear matter. The surface is so dense it could stop a bullet made of lead after a microscopic fraction of a millimeter. Beneath that crust lies a sea of neutrons packed so tightly that the whole star behaves more like a single atomic nucleus than a celestial body. It's a star stripped of all excess, reduced to its essential ingredients: gravity, pressure, and spin. And spin it does. Because the collapsing core was once vast and rotating slowly, all that angular momentum is now concentrated into a tiny space. The result is dizzying. Some neutron stars rotate hundreds of times per second, faster than a kitchen blender, completing a full turn in less time than it takes to blink. Their magnetic fields are equally extreme, trillions of times stronger than Earth's. The combination of intense rotation and magnetic energy creates one of the most extraordinary phenomena in astronomy, the pulsar. A pulsar is a neutron star that emits focused beams of electromagnetic radiation from its magnetic poles. These beams sweep through space as the star spins, and when one happens to point toward Earth, it flashes rhythmically, like the beam of a cosmic lighthouse. Each pulse arrives with astonishing regularity, repeating with the precision of an atomic clock. When the first pulsar was discovered in 1967, the signal was so perfectly timed that astronomers briefly considered the possibility it came from an intelligent civilization. They labelled it, half-jokingly, LGM, Little Green Men, before realising it was something even more extraordinary, a natural beacon run by the laws of physics alone. Since then, thousands of pulsars have been found, each ticking away in its own corner of the galaxy. Some pulse every few seconds, others more than 700 times a second. These rapid rotators, called millisecond pulsars, are often found in binary systems where a companion star has donated mass, spinning the neutron star faster in the process. They're among the most precise timekeepers in existence, rivaling human-made atomic clocks in consistency. You could in theory set your watch by them, though it might make morning alarms slightly more dramatic. Nature, it seems, has a sense of punctuality that would make any train schedule blush. The light from pulsars isn't just a curiosity, it's a powerful tool for science. By measuring the exact timing of their pulses, astronomers can detect subtle changes caused by gravitational waves, the ripples in space-time produced by orbiting black holes or colliding stars. In this way, neutron stars serve as both laboratories and instruments, extreme objects that allow us to test the deepest laws of physics. But if pulsars are the disciplined, predictable kind of neutron star, magnetars are their volatile cousins. These rare objects have magnetic fields so intense they could erase a credit card from halfway to the moon. Not that they need to, since they'd also vaporize the card holder. Their fields are quadrillions of times stronger than Earth's and can twist the very fabric of a neutron star's crust, causing sudden starquakes that release massive bursts of energy. When a magnetar flares, it can emit more power in a fraction of a second than the sun does in 100,000 years. Despite this ferocity, magnetars are short-lived in cosmic terms. Their extreme magnetism drains their rotational energy quickly, slowing them down and calming them over thousands rather than millions of years. Eventually they fade into quieter neutron stars, their tempestuous youth behind them. Yet for that brief time, they are among the most violent and mysterious objects in the cosmos. Natural engines operating on scales that test the very limits of what matter can endure. The physics inside a neutron star remains one of science's great frontiers. At such immense densities, the behavior of matter becomes uncertain. Do neutrons form exotic states, perhaps dissolving into quarks, the fundamental particles that compose them? Does superfluidity occur, allowing matter to flow without friction inside the core? No one knows for sure. Neutron stars are places where the equations of nuclear physics and general relativity collide, where human understanding begins to tremble under the strain. Even so, what we can observe is astonishing enough. Some neutron stars are surrounded by faint expanding clouds, the remains of the supernova that created them. Others race through the galaxy at hundreds of kilometers per second, propelled by the asymmetry of their birth explosions. A few orbit black holes, creating binary systems so extreme that time itself slows measurably near them, and every pulse, every flicker of light is a story, a clue to the universe's most demanding conditions. The Crab pulsar, born from a supernova seen by ancient astronomers in the year 1054, still spins 30 times per second, its beams sweeping across space like a cosmic metronome. To telescopes, it appears as a flickering source of light at the heart of a glowing nebula, a steady reminder that the energy of a dying star can last for millennia. Each rotation of that tiny remnant releases enough energy to power all the cities on Earth many times over, and yet it remains perfectly stable, ticking away as calmly as ever. For all their extremes, there's something poetic about neutron stars. They are the remnants of chaos made orderly, the ashes of a violent death shaped into precision and balance. From destruction, nature has built perfection, dense, disciplined, and enduring. They are the universe's way of keeping time, of reminding us that even in the aftermath of catastrophe, there can be rhythm. If you could hover near one, safely, somehow, you'd see nothing like a star at all. Instead, you'd face a small dark sphere spinning with incredible speed, wrapped in invisible magnetic fields that could tear atoms apart. The light from its poles would flash past like a cosmic heartbeat, unwavering and eternal. It would be both terrifying and mesmerizing, a reminder that the line between violence and beauty is sometimes impossibly thin. Neutron stars are the spinning embers of creation, small, steady and unyielding. They pulse, they flare, they test the boundaries of physics, and yet they remain astonishingly reliable. In a universe of change and chaos, they are timekeepers, storytellers, and survivors. And as long as they spin, they whisper through the dark, counting out the seconds of eternity with perfect cosmic grace. Sometimes even a neutron star cannot withstand gravity's relentless pull. When a massive star's core collapses beyond all known limits, there is no force left in nature to hold it up. The atoms are crushed, the neutrons give way, and everything that made the star, its mass, its light, its structure, falls inward toward a single point. What remains is not really an object at all, but a region of space where gravity has taken control completely. This is a black hole, the universe's ultimate victory of gravity over matter. The name might suggest emptiness, but a black hole is far from nothing. It's a place where the warping of space and time becomes so extreme that nothing, not even light, can escape. The boundary around it, called the event horizon, marks the point of no return. Anything crossing that invisible line is lost to the outside world forever. It doesn't fall into something in the traditional sense, it simply vanishes from all possible observation. From a distance, the event horizon looks perfectly smooth and still, like the calm surface of a dark pond, yet beneath it lies a mystery so profound that even our best physics begins to falter. Explaining why light cannot escape doesn't require equations, just an understanding of how gravity bends the fabric of space. Imagine space as a vast, flexible sheet. Every object with mass causes the sheet to curve around it. For something as massive as a black hole, the curve becomes infinitely deep. A well so steep that once light moves downward into it, there's no path back out. Time itself slows near the edge, stretching seconds into centuries. To a distant observer, anything falling in seems to freeze, never quite disappearing as its light grows dimmer and redder until it fades completely. The black hole, in a sense, hides time itself. Yet black holes are not silent. Paradoxically, some of the brightest and most energetic phenomena in the universe occur just outside their event horizons. When gas and dust spiral toward a black hole, they don't plunge straight in. Instead, they form a rapidly spinning disk, flattened by the immense gravity and heated to extraordinary temperatures through friction and compression. This accretion disk glows fiercely, radiating energy across the spectrum from X-rays to visible light. The process is staggeringly efficient. Matter falling into a black hole can convert 1/10 of its mass into pure energy, make it far more powerful than any nuclear reaction known. Around supermassive black holes, the titans that sit at the centers of galaxies, this accretion can create some of the most luminous objects in existence, quasars. These cosmic lighthouses can outshine entire galaxies, visible across billions of light years. From their poles, some black holes launch narrow jets of charged particles at nearly the speed of light, streaming outward for hundreds of thousands of light years. The exact mechanism behind these jets is still not fully understood, but magnetic fields seem to play a crucial role, channeling energy from the swirling disk into tight collimated beams. In these moments, black holes are not just destroyers, they are engines, sculpting galaxies and influencing the growth of stars and planets far beyond their reach. There is an elegance to how black holes merge the simple and the incomprehensible. On paper, they can be described by just a few quantities: mass, spin, and charge. Yet they affect everything around them with limitless complexity. Small ones, formed from the collapse of massive stars, weigh only a few times the mass of the Sun. Supermassive black holes, by contrast, hold millions or billions of solar masses, anchoring the hearts of galaxies like invisible dynamos. And in between lie intermediate black holes, elusive and rare, possibly formed when smaller ones combine over cosmic time. When two black holes find each other, their interaction becomes one of nature's most exquisite performances. They spiral together in a tightening dance, their motion stirring the very fabric of space-time. With each orbit, they lose a bit of energy as gravitational waves, ripples that travel through the universe itself. These waves are unimaginably faint by the time they reach us, yet sensitive detectors on Earth, like LIGO and Virgo, can measure distortions smaller than a fraction of an atomic nucleus. Each detection is a cosmic echo, a whisper of two invisible giants colliding in the dark. When they finally merge, they create a new, larger black hole that rings like a struck bell, releasing the last of its energy before settling into silence once more. These ripples are not just beautiful curiosities. They confirm that space and time are not rigid backdrops, but dynamic, living entities that can stretch and flex under gravity's touch. Every merger adds another note to the universe's quiet symphony, a deep, resonant tone that carries across billions of light years. It's as if the cosmos itself hums softly, recording the movements of its most mysterious inhabitants. Though black holes seem to erase information, they are also creators in their own way. Their influence shapes galaxies, regulates star formation, and drives cosmic evolution. Without them, the universe would be a quieter, simpler, and perhaps duller place. And there are hints that even within their apparent finality, some form of order persists. The event horizons area, for instance, behaves almost like entropy, a measure of disorder, suggesting that black holes obey a kind of thermodynamic law. Physicists have even found that, thanks to quantum effects, black holes can slowly leak energy in the form of Hawking radiation. Over immense spans of time, this process could cause them to evaporate entirely, leaving only faint whispers of heat behind. If you could hover at a safe distance from one, the view would be mesmerizing. Around the black circle of the event horizon, light from the surrounding universe would bend into perfect arcs, distorted by gravity into a glowing ring. The background stars would stretch and twist, forming halos of impossible symmetry. You'd be looking at the universe folded back on itself, beauty born from extreme gravity. And yet, for all its strangeness, a black hole is not chaos. It's one of nature's purest expressions of simplicity. Matter reduced to geometry, energy distilled into curvature. It teaches us that even darkness can have structure, even absence can have form. There's something poetic about the idea that the end of a star can become an engine of light, that the universe's most impenetrable objects can sing through gravitational waves, and that even the deepest darkness has its music. Black holes are not the villains of the cosmos, they're its composers, turning gravity into melody, silence into rhythm, and time itself into a slow, eternal refrain. When a star explodes, the story doesn't end with the flash. The blinding light fades, the roar of the supernova subsides, and what's left behind drifts outward, a vast, expanding cloud of debris that carries the memory of the star that once was. This is a supernova remnant, a luminous ghost of destruction, spreading across light years of space, glowing in the aftermath of catastrophe. For a while, it remains hot enough to shine in every wavelength, from brilliant X-rays to cool radio waves, an intricate web of light woven through the dark. At first, the gas rushes outward at millions of kilometers per hour, still glowing with the heat of the explosion. The ejected material forms a bubble, sweeping up interstellar gas and dust as it expands. What was once the outer layer of a star becomes a cosmic shockwave, racing through space like a storm front. Over time, the expanding cloud cools and slows, but its structure grows more complex. Rippled filaments, knots, and loops, all shaped by turbulence and magnetic fields. Each filament is a boundary where fast-moving gas collides with slower material, heating it until it glows. In X-rays, these regions shimmer with the energy of freshly accelerated particles. In visible light, they look delicate and thread-like, like spider silk stretched across the heavens. To telescopes, a supernova remnant is one of the most breathtaking sights in astronomy. The Crab Nebula, born from a stellar explosion observed in the year 1054, still glows vividly nearly 1,000 years later. It appears as a tangled mesh of luminous filaments surrounding a pulsar at its center, the spinning remnant of the original star's core. The Veil Nebula, older and larger, spreads across a region of the sky, big enough to fill the full moon many times over, its tendrils glowing red, blue and green as different gases emit their characteristic light. These are the embers of stars, still shining long after the fire has gone out. Yet these remnants are more than just beautiful. They're essential. The gas they carry is enriched with elements forged in the explosion. Iron, calcium, silicon, nickel, and others scattered throughout space. Each atom of these heavy elements is a relic of fusion, created in the intense pressures and temperatures of a dying star's final moments. As the supernova shell expands, it spreads those elements into the surrounding medium, blending them with the hydrogen and helium that filled the galaxy long before. Eventually, that enriched gas will cool, collapse, and form new stars and planets. Every world, every rock, every living thing owes its existence to the material released in events like these. The universe recycles itself through destruction. The shockwave of a supernova doesn't just scatter material, it also reshapes its environment. As it moves outward, it compresses the gas it encounters, creating regions dense enough to trigger the birth of new stars. In this way, the death of one star can set off the formation of many more, continuing the grand cycle of creation. The galaxy, from this perspective, breathes. Stars are born, they shine, they die, and their remains seed the next generation. Destruction and creation are not opposites here. They're phases of the same eternal rhythm. Astronomers can trace this rhythm in exquisite detail by observing supernova remnants in different wavelengths of light. In visible light, they reveal glowing filaments of oxygen, nitrogen, and sulfur. In X-rays, they show the hottest regions. Shock fronts moving at thousands of kilometers per second. In radio waves, we see the afterglow of electrons spiraling through magnetic fields, a sign of high-energy processes still at work long after the explosion. Each wavelength reveals a different chapter in the story of transformation, a different note in the symphony of decay and renewal. Inside these expanding clouds, dust grains also begin to form, tiny crystals of carbon, silicates, and metals that will later become the raw material for planets. Some of the dust survives the intense heat of the explosion, while some is destroyed and reformed in cooler regions. These microscopic fragments drift through the galaxy, eventually finding their way into new systems. It's entirely possible that the atoms in our own planet's rocks, and even in our bodies, once belonged to the dust clouds of ancient supernovae that exploded billions of years ago. When people say we're made of stardust, they are speaking literal truth. The dynamics of a supernova remnant evolve over tens of thousands of years. As it expands, the hot gas inside gradually mixes with the colder interstellar medium, losing energy and brightness. The outer edges slow down, becoming less defined, while the interior begins to fade into the background. Eventually, the once blazing remnant becomes indistinguishable from the rest of the galaxy's gas. Its identity lost, its elements absorbed into the ongoing cycle of birth and death. But by then, its purpose has been fulfilled. It has spread the ashes of a star across space, setting the stage for new worlds to rise. Some remnants, like Cassiopeia A, still crackle with high-energy radiation centuries after their birth. Astronomers studying such remnants can see not just their light, but their motion, watching the filaments drift outward year by year. The data reveal turbulence on unimaginable scales, with regions of hot plasma colliding and intertwining like slow-moving lightning. Even in their fading stages, these remnants are alive with energy, shaping their surroundings long after the initial explosion has passed. Supernova shells also serve as cosmic accelerators, powering particles to speeds close to that of light. When these high-energy particles, known as cosmic rays, eventually reach Earth, they strike our atmosphere and cascade into showers of subatomic fragments. In this way, we're connected to ancient explosions that happened thousands of light years away. The light from a supernova might take centuries to reach us, but its influence arrives continually in the form of these invisible messengers. There's a quiet symmetry in how it all unfolds. The star's life begins in a cloud of gas shaped by earlier explosions and its end becomes the seed for others to come. Over billions of years, this process builds galaxies, metals, and eventually the conditions for life. The debris we see as delicate glowing filaments is the mechanism through which the universe renews itself. It's a slow inhale and exhale, an endless recycling of energy and matter. If you could drift through one of these remnants, it would be like moving through the aftermath of creation itself. Wisps of gas would shimmer faintly in the dark, glowing with faint blues, reds, and greens. The density would be almost nothing, far thinner than the best vacuum we can make on Earth, and yet, over distances of light years, it would feel vast and alive. Each filament, each ripple, would carry the fingerprints of the explosion that birthed it. You'd be floating among the ashes of a star, and yet surrounded by the promise of new beginnings. The universe, in the end, is not a static collection of stars and galaxies, but a living process, one that grows, dies, and renews itself endlessly. Supernova remnants are the clearest evidence of that truth. They are the bridges between endings and beginnings, between death and rebirth. To watch them is to glimpse the breath of the cosmos, a long, slow rhythm where destruction is never wasted and creation is never far behind. Every atom that makes up the world around us was forged in the heart of a star. The carbon in our cells, the calcium in our bones, the oxygen we breathe, none of it existed in the earliest moments of the universe. Back then there was only hydrogen, helium, and a trace of lithium, light elements born from the Big Bang. Everything else, all the rich variety of matter that fills the cosmos today, was created later in the furnaces of stars and the explosions of their deaths. Every piece of life, every grain of dust, every drop of water is the product of stellar alchemy, the universe's slow and patient chemistry set at work. It begins inside stars, where the pressure and heat are so intense that atoms are forced to combine. In small, steady stars like the Sun, hydrogen fuses into helium, releasing the energy that makes them shine. But when those stars age and swell into red giants, their cores grow hot enough to fuse helium as well. The reactions that follow produce carbon, the backbone of all known life. In the gentle winds that blow from the surfaces of red giants, that carbon escapes into space, mingling with the interstellar gas. Over time it cools and condenses into tiny grains of dust, specks of solid matter that drift for millions of years through the galaxy, waiting to become part of something new. More massive stars push the process much further. Their immense gravity creates conditions fierce enough to fuse not just carbon and oxygen, but elements like silicon, magnesium, and iron. When these giants reach the end of their brief, brilliant lives and explode as supernovae, they scatter their contents into the galaxy at astonishing speeds. The shock waves mix the newly forged elements with the surrounding gas, enriching vast regions of space. Each generation of stars adds to this cosmic inventory, seeding the raw materials for planets, oceans, and life. The galaxy is, in essence, a giant recycling plant, a place where matter continually dies, transforms, and is reborn. Some of the universe's rarest and heaviest elements come from even more extraordinary events. When two neutron stars collide, their crash unleashes torrents of energy and spews out material rich in heavy nuclei. In these fleeting, violent moments, gold, platinum, uranium, and other precious elements are formed. The collision's debris glows briefly in ultraviolet and infrared light, then cools into clouds of dust laced with these rare metals. Every ring of gold and every trace of iodine in your body owes its existence to such cosmic violence. the jewellery in a display case, the circuit in a phone, the coins in a pocket, all were born from the collision of dead stars. Over billions of years, this galactic enrichment builds layer upon layer of complexity. Each new generation of stars forms from clouds slightly more seasoned than the last, containing more carbon, oxygen, and iron. With time, these ingredients assemble into planets. Dust grains stick together, forming pebbles, rocks, and worlds. Around young stars, swirling disks of gas and dust flatten and clump, creating planets rich in the remnants of earlier suns. Water molecules formed from oxygen and hydrogen in the cold depths of interstellar space collect on their surfaces. Metals settle into cores. Carbon compounds gather into organic molecules. Out of these quiet, natural processes comes everything familiar: mountains, oceans, air, and life. When we look at the periodic table, we're really looking at a family tree of the cosmos. Hydrogen and helium are the universe's oldest members, direct descendants of the Big Bang. Carbon, nitrogen, and oxygen come from red giants and massive stars. Iron and nickel were forged in supernovae. Gold and platinum arrived later, from neutron star mergers. Each element tells part of the story of how the universe learned to make complexity from simplicity. We are quite literally the product of billions of years of stellar evolution. Even the dust between the stars carries traces of this history. In the vast clouds of the Milky Way, molecules form on the surfaces of these dust grains. Water, methane, ammonia, simple sugars, and more. When such clouds collapse to form new stars, some of that chemistry is preserved, incorporated into comets and asteroids that later deliver these molecules to young planets. It's possible that the seeds of life on Earth arrived this way, carried by fragments of ancient cosmic dust older than the planet itself. The next time you look up at the night sky, consider that every shining point is performing this same quiet work of transformation. Each star is building the future, creating elements that will someday form new worlds, new oceans, and perhaps even new eyes to look back at the stars again. The process is so vast, so slow, that it feels eternal. Yet every atom in your body has been through it, passing from gas cloud to star, from star to dust, from dust to planet, until eventually arriving here, thinking and breathing beneath the same starlight that made it. The oxygen flowing through your blood came from a long-dead giant. The calcium in your bones once glowed in the shell of a red supergiant. The iron that carries that oxygen was born in the heart of an exploding star. The gold in a ring on your hand was forged when two neutron stars collided billions of years ago in a galaxy far from our own. And every time your heart beats, the energy that drives it comes from the fusion of atoms, the same process that makes stars shine. Every heartbeat is powered by ancient starlight. In this way, life is the universe remembering itself. We are the consciousness of stardust, the awareness that emerged from matter refined over eons. When we study the stars, we're not just looking outward, we're looking backward and inward at the same time, tracing our own origins to places we'll never reach. The atoms that once floated freely in space have learned to think, to dream, to wonder how they came to be. The next generation of stars will carry this process forward, just as all those before have done. Clouds enriched by countless supernovae and mergers are already forming new suns across the Milky Way. Each one will, in time, forge more elements, scatter more dust, and give rise to more planets. The cycle continues, a rhythm as steady as the beating of a heart. The universe breathing in and out, creating and recreating itself endlessly. The beauty of this story lies in its simplicity. Everything changes, Yet nothing is lost. The matter that once made a star now forms a tree, a river, or a living mind. When that matter moves on, it will become something else again. The stars die so that worlds can live, and worlds live so that the stars can shine through their reflection. The universe is not a place of permanence, but of flow, an endless exchange of light and life, bound together by time, energy, and memory. So when you breathe in, you're sharing atoms with long-dead stars. When you stand on the ground, you're touching ancient stardust. And when you look up at the night sky, you're seeing the process continue. New stars forming, old ones fading, and the elements of tomorrow already being made. The story of the universe is written in those lights above, and the story of life is written in the stardust within. Every star begins life surrounded by a cloud, a swirling, glittering mix of gas and dust left over from its birth. It's the debris of creation, a cosmic afterthought that refuses to stay idle. Under the gentle guidance of gravity and time, this material will transform into something extraordinary. Planets, moons, and the countless small worlds that fill the gaps between them. In these quiet, rotating disks, the architecture of entire solar systems takes shape. At first glance, it might not look like much. The disk around a young star is thin and cold, stretching for billions of kilometers and glowing faintly in infrared light. Within it, microscopic grains of dust float through hydrogen and helium gas, colliding now and then. Most of these collisions are gentle, particles brushing past one another, sometimes sticking through the tiniest hints of electric charge or surface tension. It doesn't sound like much of a beginning, but over millions of years those tiny encounters add up. Grain by grain, clump by clump, dust becomes pebbles, pebbles become rocks, and rocks become worlds. This process is called accretion, and it's one of nature's most patient works. The same physics that guides raindrops falling from clouds governs the growth of planets from dust. As the pieces grow, their gravity strengthens, pulling in more material and accelerating the process. Eventually, some reach sizes large enough to reshape themselves into spheres under their own weight. These are planetesimals, the seeds of planets, scattered throughout the disk like marbles in a vast fog. Some collide and merge, others shatter apart, feeding the cycle again. It's a messy, chaotic process, but one with a remarkable sense of purpose. Closer to the young star, where temperatures are high, only rock and metal can survive without vaporizing. This is where the terrestrial planets form, small, dense worlds like Mercury, Venus, Earth, and Mars. Farther out, where it's cooler, ice can condense, allowing larger bodies to form quickly. These become the gas giants, Jupiter, Saturn, Uranus, and Neptune, enormous planets surrounded by systems of moons and rings. Between these regions lies a boundary where the nature of materials changes dramatically, shaping the layout of an entire solar system. As planets grow, they begin to carve paths through the surrounding gas and dust. Their gravity clears lanes in the disk, creating gaps and rings that we can now observe directly in young systems using powerful telescopes. These clearings are the signatures of new worlds being born, invisible planets revealing their presence by the structures they leave behind. Over time, the orbits of these planets stabilize, falling into resonant patterns that can last for billions of years. Gravity, at first a force of chaos, becomes the architect of harmony. Not all material finds a home in planets, though. Some remains as leftovers, orbiting the star in belts and clouds. In our own solar system, These remnants are the asteroids and comets, small, irregular bodies that carry the fingerprints of the early solar nebula. Asteroids are rocky fragments that never joined a planet, while comets are icy travellers from the cold outer reaches. When their orbits bring them close to the Sun, their frozen surfaces vaporize, creating glowing tails that stretch across the sky. They are fossils of the solar system's youth, preserved reminders of how it all began. The formation of planets is not a single smooth story. There are collisions, migrations, and near misses on unimaginable scales. Early in its history, Earth itself likely endured a cataclysmic impact, with another young planet roughly the size of Mars. The collision melted both worlds and ejected debris that eventually coalesced into the Moon. Farther out, the giant planets may have drifted from their original positions, disturbing the orbits of smaller bodies and reshaping the solar system's structure. Even now, the asteroid belt bears the scars of those early disruptions, a region that might have become a planet if Jupiter's gravity hadn't constantly interfered. Despite all the chaos, the end result is order. A family of planets circling their star, each in a stable orbit, each following the same rules of motion that governs galaxies and atoms alike. The process takes tens of millions of years, but it happens again and again throughout the cosmos. Around distant stars, astronomers have found countless disks that look strikingly familiar, some with dark gaps where planets are forming, others already home to mature systems of strange and beautiful worlds. Some orbit twin stars, others blaze under the light of red dwarfs or giant suns. Yet the pattern remains the same. Dust gathers, grows, and becomes a home for the future. The discovery of thousands of exoplanets has shown that planetary formation is not rare or delicate. It's the universe's default behaviour. Wherever there's a young star and a supply of gas and dust, planets seem eager to appear. Some are giant worlds that orbit scorchingly close to their stars. Others drift through the cold outskirts wrapped in ice. Some may host water, continents, and clouds. Others are endless oceans or spheres of gas with storms larger than Earth itself. The diversity is staggering, but the underlying story is the same everywhere. From dust, order arises. The materials that make up these planets are the same that once drifted through the galaxy as stardust. The iron in their cores, the carbon in their atmospheres, and the water in their oceans were all forged long before the planets existed, born in the hearts of earlier generations of stars. When a new solar system forms, it inherits the chemistry of its ancestors. Every world is a continuation of the same cosmic story, an echo of past lives written in metal, rock, and ice. Even the smallest fragments, comets wandering on long looping orbits, carry traces of this shared history. When they approach their stars and begin to glow, they release material older than the planets themselves, offering clues to the conditions that existed before formation began. Some of those comets, in the early history of our own world, likely brought water and organic molecules to Earth, seeding the ingredients for life. In that sense, they are messengers from the past, carrying the universe's oldest stories into every sunrise and raindrop. The elegance of it all is that the same laws shaping these distant systems also shaped us. The same gravity that pulled grains of dust into clumps now holds Earth in orbit. The same chemistry that filled the disks of ancient stars fills our air and blood. Across the galaxy, billions of young stars are encircled by the same slow dance of particles, quietly building their own versions of home. If you could stand in one of those forming systems and watch it unfold, you would see a scene of serene chaos, thin clouds of dust glowing in the starlight, rings and gaps forming where new planets carve their paths, fragments colliding and merging in graceful arcs. It would be like watching a time-lapse of creation, sped up across eons, the moment when disorder learns the language of balance. From dust to planets, from chaos to harmony, the process repeats endlessly. Every new star is a sculptor, every ring of dust a promise of something to come. And somewhere out there, among the countless worlds being born right now, perhaps another Earth is gathering shape. A world of oceans and skies, waiting for its own sunrise. The same process that made our planet is happening across the galaxy, quietly, beautifully, and without end. The universe, for all its vastness, is still young. Our galaxy is busy and bright, filled with the light of hundreds of billions of stars. Nebulae bloom, planets form, and supernova flare like cosmic fireworks. Yet this brilliant age of starlight will not last forever. Every fire eventually dims, every rhythm slows, and though it will take far longer than any human mind can truly grasp, the cosmos itself will one day grow quiet. The story of the stars, so full of heat and motion now, will end not with a bang but with a whisper. In that far-off era, long after our sun has faded, the most enduring stars will still shine. These are the red dwarfs, small, cool, and astonishingly efficient. While massive stars race through their lives in a few million years, red dwarfs burn their hydrogen so slowly that some could last for trillions. The universe is only about 14 billion years old, which means not a single red dwarf has yet reached the end of its life. They will glow dimly for eons, gradually reddening and fading, becoming fainter and cooler until they turn into dark, invisible remnants. In the twilight of the cosmos, when all else has gone dark, their soft glow will be the last light still shining. Meanwhile, the larger stars that once filled the galaxies will have long since met their fates. Their remnants, white dwarfs, neutron stars, and black holes, will linger for inconceivable stretches of time. White dwarfs, those hot, dense cores left behind by ordinary stars, will slowly radiate away their heat. Over billions of years they will cool and solidify from the inside out, their matter crystallizing into immense cosmic diamonds. In the distant future, galaxies will be filled not with blazing suns, but with these quiet gems of carbon and oxygen, shining faintly before they too fade to black. Neutron stars, the collapsed hearts of supernovae, will also cool, their fierce magnetism and radiation slowly declining. They will spin more and more slowly until their pulses cease, becoming dark, frozen monuments to the stars that once were. And black holes, those most enigmatic of remnants, will continue their silent reign, swallowing dust, gas, and even other black holes, merging into ever larger giants. Over trillions of years, galaxies will gradually lose their stars through gravitational interactions, and their centers will be ruled by immense, quiet black holes. But even black holes are not forever. According to the theory of Stephen Hawking, they will slowly lose mass through a subtle process known as Hawking radiation. This radiation is incredibly faint, so faint that for now it is beyond our ability to detect. But it implies that black holes can, in time, evaporate entirely. For a black hole with the mass of a star, that evaporation would take roughly 10 to the power of 67 years, a number so enormous it barely fits into language. For supermassive black holes, the process is even slower, stretching into unimaginable depths of time, far beyond the lifespan of any star, galaxy, or atom. Before that happens, however, the galaxies themselves will change. Star formation will gradually slow as the gas needed to make new stars is used up or locked away in remnants. Fewer and fewer bright young stars will be born, and those that remain will grow old. The spiral arms of galaxies will fade, their colours shifting from blue and white to dull red, then to grey. The Milky Way and its neighbours will merge into a single, quiet, elliptical galaxy, where the last red dwarfs will flicker in the darkness. After a few trillion years, even those lights will wink out. The night sky of that future universe would be strange and nearly empty. The bright constellations that fill our skies now will have vanished, their stars long gone or drifted apart. The nearest galaxies will have merged into faint smudges, while the more distant ones will have receded beyond visibility, carried away by the ongoing expansion of space. Future observers, if any exist, may look up and see only the fading afterglow of their own local stars, unaware that a vast cosmos once lay beyond. Eventually only remnants will remain, the cold ashes of stars, the quiet remnants of collapse, and the scattered dust of worlds long gone. Matter will continue to drift, but more and more of it will end up trapped in black holes. As those black holes merge and grow, they will dominate the final era of cosmic structure. When even they begin to evaporate, the last energy of the universe will return to space as faint, uniform radiation. The temperature of the cosmos will fall ever closer to absolute zero, and motion itself will slow. It will be an age of stillness, an age of endings. But this long fade is not a tragedy. It's simply the natural conclusion of a story that began with fire. The universe has been a vast engine of creation for billions of years, a system that built stars, planets, and life from nothing more than hydrogen and time. The fact that it will one day rest does not diminish its beauty. In a sense, the cosmos will have earned its sleep. After its long labour of creation, after forging galaxies and minds capable of wonder, it will finally fall silent, not in defeat, but in peace. Even in that distant darkness, traces of its history will endure. Photons, the particles of light released long ago, will continue to drift across space, growing colder and longer in wavelength but never quite vanishing. They are the memory of everything the universe has ever done. The atoms once part of stars, worlds, and living beings will still exist, though scattered across unimaginable distances. In that eternal quiet, the universe will still be, in its own way, alive, not in light and heat, but in continuity. If one could somehow witness this distant epoch, it would look serene. The last faint glows of fading stars, the occasional flicker of a merging black hole, the slow sigh of heat spreading evenly through space. It would be the universe breathing its final breath. And then, after incomprehensible ages, even that faint glow would dim. The cosmos, once vibrant with colour and motion, would settle into perfect darkness. Yet there is a strange comfort in this ending. The atoms that make us, the light that warms us, and the stars that guide us have all been part of this grand cycle. Their eventual rest is not loss but fulfillment, the quiet conclusion of a long and intricate story. From the first spark of creation to the last glimmer of light, the universe has been a masterpiece of balance, born from chaos and destined for calm. And when that final red dwarf flickers out, when the galaxies fall silent and the last black hole exhales its final whisper of heat, the cosmos will rest, vast, still, and complete. After its endless work of creation, the universe will finally close its eyes, content to sleep among the stars it once made, from darkness to light and back again, That is the quiet rhythm beneath everything. In cold, hidden clouds, gravity gathers scattered atoms and teaches them to hold one another. Those drifting veils fold into knots. Knots glow into embers, and embers kindle into stars. For ages they keep their steady balance, turning the simplest elements into warmth and colour. Then, when the balance finally tips, they exhale. Some loosen their outer layers in soft, luminous shells. Others end in a single bright heartbeat that outshines a galaxy. What drifts away does not vanish. It becomes the raw material of what comes next. The ashes of old suns seed new nurseries. Carbon made in gentle giants mingles with oxygen forged in short-lived titans. Shock waves comb through the haze, stirring filaments and beads where gravity can begin again. Dust grains form, drift, and carry with them a memory of every fire that came before. In time, around young stars, those grains learn to stick, to gather, to become rocks and worlds. Water condenses, atmospheres rise, the chemistry of clouds turns into the chemistry of oceans and rain and breath. It is one story told many ways. Clouds collapse, stars shine, stars die, and their remnants build new worlds. Nothing in this cycle is wasted. Light born in a core takes a long, patient path outward, meets dust, and is scattered into soft glow. The dust itself returns to gas and then back to dust again. Atoms travel in great arcs, from nebula to star, from star to nebula, from nebula to planet, changing partners but never losing themselves. Even endings are acts of generosity. A red giant's winds enrich the space between the stars. A supernova's blast forges and flings rare elements far and wide. A merger deep in the dark writes gravity's music across the universe, ripples that slide through everything and gently keep time. Look closely and the same pattern appears everywhere. In the spiral arms of a galaxy, starbirth follows the trails of older explosions. In a planetary disk, gaps and rings sketch the orbits of worlds still forming. In the glow of a remnant, delicate filaments trace the energy of creation passing into its next form. The universe breathes, a long inhale of gathering, a long exhale of release. The breath is measured not in seconds, but in eras, yet the motion is always there, quiet and sure. We are part of that motion. The calcium in your bones was forged in the shell of a dying star. The iron that carries oxygen through your blood once lay at the heart of an ancient sun. The carbon that shapes your thoughts and the oxygen you draw in with each breath are gifts assembled in stellar furnaces and delivered by stellar endings. Even the gold woven into a ring traces back to the brief, brilliant moment when two neutron stars collided and scattered heavy atoms into night. To say we are stardust is not poetry but simple fact, and still it feels like wonder. There is comfort in the constancy of it all. Stars rise and fade, galaxies drift and merge, and yet the rules that guide them remain patient and dependable. Gravity gathers, fusion gives, light travels, matter transforms but is never lost. Across the widest distances, the same physics that brightens a newborn star also sets the rhythm of your own heart. Every quiet inhale, every slow exhale is powered by energy that began as sunlight, which began as the joining of the smallest things into something new. Every heartbeat is powered by ancient starlight. If you carry that thought outside under the night sky, the view changes. The dark is not empty, it is a garden at rest. The bright points are stories mid-sentence. Some are young and hot, some are steady and middle-aged, and some have already sent their last light on its long journey toward you. Between them, in places that look like nothing at all, new stars are waiting to begin. The sky is not a map of fixed lights. It is a living history, a slow symphony where every note becomes the next. In the far future, the pace will slow. Star formation will ease. Red dwarfs will hold their gentle glow for trillions of years, and remnants will cool into quiet embers. Even black holes will one day release their last whisper of heat. The cosmos will rest after its long work of creation, yet even that rest carries the shape of the story we know. Energy diffusing, matter dispersed, nothing wasted, everything accounted for. So let this be the calm you take with you to sleep. You are made of durable things, borrowed for a while from a generous universe. The atoms that compose you have survived storms fiercer than imagination, and journeys longer than memory. They will go on, learning new forms, writing new chapters, long after tonight's thoughts have settled. You're a brief arrangement in an ancient dance, real, precious, and connected to everything that ever shone. Look up once more before you close your eyes. The light that reaches you has travelled a very long way to keep you company. It carries news of beginnings, of endings, and of all the quiet spaces in between. The stars above you tonight are both your ancestors and your future.